Hello everyone and God bless you. Welcome to this new series. Actually, this video, okay, it will be one piece at first on all types of integrals, starting from the simple integral all the way to double, triple integrals, surface integrals, even the advanced stuff. I hope that you would enjoy it. It would be mainly practical because it is way better to learn through practice. You learn way better as you practice these things. Not only watch these exercises being solved, but also try to solve them on your own. And this is how you get to build up yourself in those stuff, okay, concerning everything on integrals. So let's get started. First problem, basic antiderivative. Find integral of 7x6 dx. Now for each problem, you can get to pause the video, try to solve the problem yourself, and then get back to the solution. So this goes for all the exercises that we're going to see in this video. So integral x 6 times 7 dx, using the power rule, this is how we solve it. Integral of x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus c. So you add 1 to the power and you divide the power that has been added with 1 over x in such case. Therefore, integral of 7x6, by the way, given that 7 is a constant, you can remove it to the outside of the integral. dx, which is 7, x7 divided by 7 plus c, or x7 plus c. Evaluate integral 12 dx. By the way, this can be written as 12 times x to the power of 0 dx. Because x to the power of 0 or anything to the power of 0 gives us 1. So the integral for that is x to the power of 0 plus 1 over 1, which is 12x plus c. So again, the integral of a constant is given by ax plus c. Hence, integral of 12 dx is equal to 12x plus c. And c is a constant, the constant of integration, by the way. The sum rule. Integral of a sum is equal to the sum of integrals. In other words, integral of 4x3 plus 2x minus 5 dx can be equated or rewritten as integral of 4x3 dx plus integral 2x dx minus 5, because any constant can be removed outside of the integral, times integral dx, which is 4x4 divided by 4 plus 2x2 divided by 2 minus 5x plus c. You leave the constant till the end, okay? Or you can write it as 4x4 divided by 4 plus c1, as if that's the constant of the first integral, plus 2x2 divided by 2 plus c2 minus 5x plus c3, with c being c1 plus c2 plus c3, okay? So you can factor out here 4 and 2, so you end up with x4 plus x2 minus 5x plus c. So again, you can integrate each term separately. 4x3 gives us x4, because 4x4 divided by 4. Integral of 2x dx gives us x2. And that of minus 5 dx gives us minus 5x. Combining results, you end up with x4 plus x2 minus 5x plus c. Exponential function. So let's say you have integral of EU du. This is how you solve the integral. It is equal to u prime, derivative of u, multiplied by EU plus c. So here, integral ex would simply give you derivative of x, which is 1, times ex plus c. So since derivative of ex over dx is equal to ex, because derivative of x again is equal to 1, okay, it follows that integral ex dx gives us ex plus c. natural logarithm, integral of 1 over x dx. Now remember that derivative of ln x gives us du over u for ln u, okay, which is dx over x, or 1 over x. Now, the integral is the entire opposite for that. So, it has the form of integral du over u is equal to ln u plus c plus a constant. So, if u is equal to x, like here, du is equal to 1. And this is the form. This is the form of integral du over u, which is dx over x in our case, equal to ln x plus a constant. Again, as we stated, since the derivative of ln x in respect of x is equal to 1 over x, then the integral is the exact opposite. So the integral of 1 over x gives us ln x plus a constant. Trigonometric function. We know already that derivative of cosine x gives us minus sine x. But for the integral, it gives us plus sine x. So integral cosine x dx is equal to plus sine x plus c, okay? Given that, why? It is simply because that the derivative of sine x in respect of x gives us cosine x. So the integral, another name for it is the antiderivative. So it is equal to the function for which the derivative gives us this value. So integral cosine x dx is equal to sine x. Why? Because the derivative of sine x in respect of x gives us cosine x. I hope that it has become clear by now. The same thing for integral of sine x dx. You know that the derivative of cosine x in respect of x gives us minus sine x. Hence, the integral of sine x dx is minus cosine x plus c. Let's check it out. So derivative of minus cosine x in respect of x is equal to sine x. Or you can say derivative of cosine x in respect of x is equal to minus sine x. Then you multiply the minus to the left. Hence, integral sine x dx is equal to minus cosine x plus c. Evaluate integral of sinh x dx, which is the hyperbolic function. Now, for most of these things, you need to memorize the basic formulas. So, for integral of sine h x or sinh x dx, we know that the derivative of cosine h, you can pronounce it or spell it as cosh x, gives us sinh x. Hence, integral of sinh x dx, which is the hyperbolic sine, gives us cosh x plus c. Another way to approach this method is to use the formula for sinh x, because we know that sinh x can be written as ex minus e minus x divided by 2. And we know, by the way, that cosh x is equal to ex plus e minus x divided by 2. So let's solve the integral in this way. So integral sinh x dx is integral ex minus e minus x over 2 dx. You can get rid of the 1 over 2 to the outside, moving it to the outside of the integral. Integral ex minus e minus x dx, which is solved as, okay, integral ex gives us ex simply. Now integral of e minus x, remember integral eu du is equal to u prime e u plus c, correct? So integral of minus x, what is the derivative of minus x? Minus 1. So this minus 1, you multiply it behind the exponential with this minus 1 over here. So you end up with ex plus e minus x plus c, which is simply cosh x. This is the same formula for cosh x. This is why integrals of sinh x dx gives us cosh x plus c. Verify an antiderivative. So verify that f of x is equal to x5 over 5 is an antiderivative of f of x is equal to x4. In other words, to speak it in a different way or language, it is saying that verify the derivative of f of x gives us back lowercase f of x. Or in other words, d f of x in respect of dx, derivative of f of x in respect of x, is equal to lowercase f of x. So how do we actually get that? Okay, derivative of f of x is equal to 5 x4. At first you get rid of the 1 over 5, which is a constant, to the outside, okay? It is the derivative of x5, which is 5 x4, correct? So 5 times x4, you factor out 5 and you are left with x4, which is this quantity over here. Hence, fx prime is equal to f of x, or f of x capital is the antiderivative of lowercase f of x. So fx prime is equal to derivative of x5 over 5 in respect of x, which is equal to 5x4 over 5 equal x4. Since f prime of x is equal to lowercase f of x, the function is indeed an antiderivative. So f of x is equal to x5 over 5 is an antiderivative of x4. Find all antiderivatives of f of x is equal to 6x. So you simply integrate f of x dx is equal to 6x2 over 2, because here you have x to the power of 1. So you add 1 and then you divide by the overall power, which is 1 plus 1 also, okay? Or x2 over 2. So 6x2 over 2. We factor out 6 and 2. You end up with 3x squared plus c, where c is a constant. So for every value of c, you can get a new antiderivative. Again, in a neat form, integral 6x dx is equal to 6 times x squared over 2 plus c, which is 3x squared plus c. These are all antiderivatives that you can have many versions of them for any or each value of c, which is a real constant. Find the function f of x such that f prime of x, or the derivative of f of x, okay, is equal to 4x3 and f1 is equal 10. So here we have a value, okay, for f to get the value of the constant. That's why. So how do we go about it? How to solve it? Now, f prime of x is equal to 4x3, correct? So f of x is the antiderivative of f prime of x dx equal integral of 4x3 dx, which is 4x4 divided by 4 plus c, which is x4 plus a constant. Now we need to find the value of that constant. Okay, now remember that f of 1 is equal 10. So f of 1 equal 10 means that for this value of f, or for x equal 1, f is equal to 10. So you place in this equation, which is f of x equal x4 plus c, for f you replace it by 10, and for x by 1 plus c. Hence c equal 10 minus 1, which is 9. So f of x finally is equal to x4 plus c, which is 9, because we have a value, okay? And this is the result in a neater form. So f of x is equal to x4 plus c. Again, you replace f by 10, x by 1. We got the value of c. You place it back in the solution. Then f of x is equal to x4 plus 9. Find the area under f of x is equal to x between 0 and 2. First of all, to give you a notion on how the integral evaluates the area between a curve and the x-axis. Actually, when you have a curve, f of x, let's say, and what the sum does, okay, when we evaluate integral of f of x dx, this is what we're actually doing. You're taking a small step dx each time at each iteration, and you're multiplying it by the height of the function at that point, which is f of x. Now, f of x times dx would give you the area of the rectangle. Now, of course, as dx gets smaller and smaller, you would get more accuracy, because let's say if dx was this big, okay? Let's say this is dx. Now, it would only give you accuracy when the function is flat. However, when you have an area like this one here, okay, a zone like this one, and this is dx, as dx is multiplied by fx, it would give you the area of the rectangle, but you would miss out on this chunk where a part would be missing from the area. So this zone over here would be missed. So you would get an inaccurate result for the evaluation of the area. However, dx is meant to be very small. So for each step, we're multiplying dx with fx to get the area of the rectangle. Then, after that, you multiply dx by the next f, the next value of the function f. And you keep adding up. This is why it's called a sum, an integral. You're integrating, you're adding up all of these areas for each and every rectangle throughout the interval to sum up the overall area between the curve itself and the x-axis. This is how it's working. Now, going back to f of x is equal to x, remember that this is the first bisectrous, meaning that the plot of this line is that for each x, you have an equal y value, okay? So from 0 to 2, you have also the same height for y. Why? Because y is equal to x at each point. So you have the side from 0 to 2, and which is the length, okay, the x length. As for the height, the same thing for x is equal to 2, y equal to also. Now, what would be the area of that zone? It would simply be the area of half of the square. The square having equal sides of 2. What is the area of the square? It is side multiplied by the other side, or side square, okay? So let's say that the side of the square has a length a. The area of the square is equal to a square. But here we have half of the square. Hence, the area for that half, which is this rectangular triangle, it would be a square over 2. Okay? Which is base square over 2 for the triangle. So, hence the formula for f of x is equal to x. That's why it is x squared over 2 plus c if you don't have sides, if you don't have upper and lower boundaries. But since we have upper and lower boundaries, it would be integral from 0 up to 2 of x dx equal x squared over 2 between 2 and 0. You place back these boundaries. So this is, by the way, f of 2 minus f of 0. This is how you evaluate it. Equal f of 2 is equal 2 squared divided by 2, which is 4 over 2, or 2. Minus f of 0 is equal to 0, because if you place 0 in x, you end up with 0, which is equal to, and this is the final result. Again, this is the area. It is equal to x squared divided by 2 between 2 and 0, which is 2 squared over 2 minus 0, or 2 square units. Polynomial integration. Integral of 5x4 minus 3x squared plus 8 dx. Again, as a reminder, the integral of a sum is the sum of the integrals. Okay, it is equal to integral 5x4 dx minus, you can leave the minus outside, 3x squared dx plus 8 integral dx, because 8 is a constant, no need to place it on the inside, equal, and you can simply straightforward solve them all, okay, without having to place an integral before each one part of the sum. So equal to 5x4 gives us 5x5 divided by 5 minus 3x3 over 3 plus 8x plus c, which is equal to x5 minus x3 plus 8x plus c. So integral 5x4, here he broken them down one by one. This gives us x5, this minus x3 because 3 is factored out, and this 8x. So x5 minus x3 plus 8x plus c. Determine the integrand. Find f of x if fx, which is capital Fx, equal to x4 minus 7x plus 3, which is the antiderivative of fx. So how to get fx? Fx would be simply the derivative of capital F of x. Okay, can be written also as dfx over dx equal to 4 times 2, which is 8x3 minus 7, okay? Because since f is the antiderivative of f of x, in other words, f of x is the integral f of x, of lowercase f of x. Hence, f of x lowercase would be the derivative of capital F of x, or df of x in respect of x. So usually, capital F of x is the annotation for the integral. Again, we differentiate, or we get the derivative of f prime x in respect of x. So, which is 4 times 2, 8, x3 minus 7. Okay, this is the main function, or the original function. As a reminder, the derivative is for x of n equal to n times x to the power of n minus 1. This is the derivative of x. So you multiply by n behind x and you subtract 1 from the power. Mixed elementary functions, so integral of 3x squared plus ex plus cosine x dx. So again, the integral of a sum is the sum of integrals. You simply get the integral for each one of these 3 elements. No need to break it down like this. You can straightforwardly solve it. So integral 3x squared dx is equal to 3x3 divided by 3, which is x3. Integral ex dx is equal to ex, and that of cosine x ds is equal to sine x. Hence, the answer is x3 plus ex plus sine x plus c. Always don't forget about the constant, very important. Evaluate integral of 5 over x dx. Now, 5 is a constant, can be removed to the outside of the integral, and you end up with 1 over x dx. Or can be written as 5 integral of dx over x. What is this form? Remember, ln x prime, derivative of ln x, is equal to dx over x. Okay, or in general, ln u, the derivative for that, is equal to derivative of u prime, over u, or du over u. Hence, this gives us 5 times ln x plus c, which is integral of dx over x. Derivative of x over x gives us ln x. So you get integral of 1 over x dx is equal to ln x, an absolute value by the way, plus c. And since it is multiplied by 5, which is a constant, 5 is removed to the outside of the integral, you end up with 5 ln x plus c. Definite integral of a constant. Okay, so the constant is removed to the outside. And by the way, as this becomes integral between 2 and 7, it has upper lower bounds of the x. Okay, integral of the x is like saying integral of x to the power of 0 dx. Given that x to the power of 0 or anything to the power of 0 is 1. So what would be the answer for that? It is x to the power of 0 plus 1 over 0 plus 1, which is x. So this is 4 on the outside, doesn't matter, multiplied by x between 7 and 2, which is 7 minus 2. 4 times 7 minus 2. 5 times 4, which is 20. So 4x, it becomes 4x between 7 and 2. 4 can be removed to the outside, which is 4 times 7 minus 2, which is f of 7 minus f of 2, by the way, equal 28 minus 8 equal 20. So hence the answer is 20. Let's evaluate integral of x3 plus 1 over x minus sine x dx. So each one apart, and you can solve them all together in one line. No need to break them down like this. Equal x4 over 4. Integral of 1 over x gives us ln x. And integral of sine x dx gives us, this alone gives us minus cosine x. Since it is multiplied by minus, so it becomes plus cosine x. Hence, the answer is x4 over 4 plus ln x plus cosine x plus c, which is the constant. Integral of x8 dx. Again, going back to the simple rule, which is integral of x to the power of n equal xn plus 1. X to the power of n plus 1 divided by n plus 1 plus c, which is x to the power of 9 over 9 plus c. Polynomial function, evaluate integral of 6x5 minus 4x2 plus 7 dx. Also, 6x6 to the power of 6 divided by 6 minus 4x3 over 3 plus 7x plus c. So this gives us 6x6 over 6, which is x6 here, minus 4x3 divided by 3 and 7x, and we add them all together with the constant. Exponential function, integral ex dx is equal to ex plus c. Why? Because, as a reminder, integral of e to the power of u du is equal to u prime, which is the derivative of u, multiplied by e to the power of u. So here u is equal to x, u prime, or du over u, in other words, is equal to 1. Hence, the integral of ex is equal to ex dx, of course, equal to ex plus c. Hence, the answer ex plus c. The same principle for integral 9ex dx. So 9 can be removed to the outside. You end up with 9 times ex, okay, 9ex plus c. Constant is at the end. So 9 integral ex dx is equal to 9ex plus c. Integral of secant square x dx. In order to solve this type of integral, we need to refer back to the trigonometric equations and formulas. So we know that the derivative of tan x, tangent x, in respect of x gives us secant square of x. Now, if we work with this one, okay, so let's place it. By the way, this is another style of thinking about it. So derivative of tan x in respect of x is equal to secant square x. If we multiply the x with the extremum here to the right side, so you get derivative of tan x is equal to secant square x times dx. Let's integrate both sides. So integral of d tan x is equal to integral to secant square x dx. What is the integral of the derivative? It's simply equal to the function itself, because they kind of annihilate each other. They kind of cancel each other out. So integral of derivative of function is equal to the function itself. Hence, you get tan x is equal to integral of secant square x dx. Tan x plus c, of course. Okay, so secant square x dx is equal to tan x plus c. And this is the neat answer here. So d tan x over dx is equal to secant square x. Hence, the integral of secant square x dx gives us tan x plus c. The same thing for integral of cosecant square x dx. You know that the derivative of cotan x in respect of x gives us minus cosecant square x, correct? So, hence, the integral of cosecant square x dx gives us back minus cotan x, okay? So you multiply minus by both sides of the equality, and this is how you can easily get the answer. So it gives us back minus cotan x plus c as an answer. And again, so you can break it down into derivative of cotan x over dx is equal to minus cosecant square x. So the x, you remove it from here, you multiply it here, minus cosecant square x dx. We multiply minus both sides, so you end up with plus here and minus here. Let's integrate both sides. So integral of cosecant square x dx gives us minus integral of the derivative of cotan x, of course, which gives us minus cotan x plus c, which is a constant. Integral of cosh x dx. Okay, so what would that give us? We know that the derivative of sinh x in respect of x gives us cosh x. And you can memorize it by formula, of course. So integral of cosh x, okay, dx gives us back sinh x plus c. As a reminder, cosh x is equal to ex plus e minus x over 2. So if you integrate it even in terms of this formula, plus e minus x over 2, you get dx, of course. So 1/2 can be removed to the outside, and then integral of ex gives us ex, and that of e minus x gives us e minus e to the power of minus x, which is what? Sinh x, okay, plus c. Don't remove or don't forget the constant at the end. Find all antiderivatives of f of x is equal to 12x squared. So integral f of x dx is equal to 12x3 divided by 3, which is 4, because 12 over 3 is 4. x3 plus c, which is the constant. So integral 12x squared dx is equal to 12 times x to the power of 3 divided by 3 plus c equal 4x3 plus c. And these are all the families of that antiderivative. Why? Because for each different value of c, you can get a new equation. Find the function f of x satisfying f prime of x is equal to 5x to the power of 4, and with f of 1 is equal to 12 as an initial condition. This is how they call it. So f prime of x is equal to 5x4, hence f of x would be the integral of f prime of x dx, which is 5x to the power of 5 over 5 plus c. So f of x is equal to x5 plus c. And we need to get the value of c. Again, f of x is equal to x5 plus c. We know that f of 1 is equal to 12, given by the proposition itself. So 12, you place it in the side of f of x is equal to 1, which is the value of x here, to the power of 5 plus c. Hence, c is equal to 12 minus 1, which is 11. Okay? Therefore, f of x is equal to x to the power of 5 plus c, which is 11. So x5 plus 11. Another example, f prime of x is equal to 3x squared minus 4, and f2, which is the initial value, it's called, is equal to 7. Meaning that for y equals 7, x is equal to, once you get f of x. At first, f of x is the integral of f prime of x dx, which is equal to integral of 3x squared minus 4 dx, of course, on the outside, which is 3x3 over 3, or x to the power of 3 minus 4x plus c. Now, we need to place the initial value. So, f should be swapped with 7, and everywhere you have x, you need to flip it with 2. So 7 equal 2 to the power of 3, which was x to the power of 3, minus 4 times x, or minus 4 times 2, plus c. So this is 8 minus 8 here, 0, and 7 on the outside, hence c equals 7. So f of x is equal to x3 minus 4x plus 7. Determine the integrand. Find f of x if f of x capital is equal to 7x4 plus 2x3 minus 9x plus 1. Okay, the integrand means that f of x is actually the integral for that function. Hence, lowercase f of x or small f of x would be the derivative. So let's check it out. So in other words, f of x would be f of x prime, or df of x, derivative of f of x in respect of x. So f of x is equal to f prime of x, which means if we want to solve it here neatly, f of x is equal to 7x4, meaning 28x3 plus 6x squared minus 9. Therefore, f of x is equal to 28x3 plus 6x squared minus 9. Another example, integral of 4x3 plus ex plus sin x dx. You can simply solve each one apart. Actually, you can solve them all together in one line, just to simplify it. So it gives us integral of 4x3 dx is equal to 4x4 divided by 4, or x4. Integral ex gives us ex, and integral of sin x gives us minus cosine x. Thus, the final answer is x4 plus ex minus cosine x plus c. Integral of 3 over x plus cosine x dx. Of course, for each example, you can pause and try to solve it yourself. Now let's move. So integral of 3 over x. 3 can be removed to the outside, so you end up with integral of dx over x, which is ln x. But don't forget to multiply with 3, which was removed to the outside. And integral of cosine x dx is equal to sine x. Hence, 3 ln x plus sine x plus c. Always remember the constant. Find all functions whose derivative is 8x to the power of 7. Now, I understand that at this point, it has been probably mixed up on you. When should we get the derivative and when should we get the integral? Okay, so how can we set them apart and differentiate between them? No pun intended. So let us break down what he's talking about. Find all functions whose derivative, so the derivative of those functions in respect of x, of course, is 8x to the power of 7. So we need to find f of x. Here we have the derivative of f of x in respect of x is equal to 8x 7. So at first, let's multiply the x to the right side. So you get df of x is equal to 8x to the power of 7 dx. We simply multiplied the x on the right side of the equality. Second step, we need to integrate both sides. So integral of dfx is equal to integral 8x7 dx. Integral of the derivative is simply the function itself. So integral of the derivative of f gives us simply f, which is actually what we have been looking for to begin with. So f of x is equal to integral 8x7 is simply 8x to the power of 8 divided by 8 plus c equal x to the power of 8 plus c. And this is the set of all functions for which the derivative is 8x7. Why we have many functions? Because c is a constant value, and for each value of c you have a new equation, a new function. This is why it's a set of functions, not only one. Now this is the straightforward way. Integral 8x7 dx is equal to 8x8 over 8 plus c, so equal x to the power of 8 plus c. Evaluate integral of minus 11x4 dx. This is straightforward. It is equal to minus 11 times x to the power of 5 divided by 5 plus c, okay, which is minus 11 over 5 x to the power of 5 plus c. Try to work on this one. Integral of 2x5 minus 4 over x plus 3ex minus sin x dx. So this is simply, okay, 2x5 gives us 2x6 over 6 minus 4, okay, integral of 1 over x, correct, which is ln x, plus 3ex. Integral of sine x gives us minus cosine x, and you have a minus here, so plus cosine x plus c. And here we can factor out 2, so you end up with 6 over 2 is 3. So starting with x6 over 3 minus 4 ln x plus 3x plus cosine x plus c. Term by term again, integral of 2x5 is x6 over 3. Here minus 4 ln x, 3x, and cosine x. So x6 over 3 minus 4 ln x plus 3x plus cosine x plus c. Differential notation. Here we've already covered how to play with the differential. Okay, so we already had given some examples concerning that. So how to solve, and this is the simple notation of a differential equation. You have dy over dx is equal to 9x squared. So how to solve it? At first, we need to multiply the x to the right side. So we said the y parts on one side and the x parts on another. You end up with dy is equal to 9x squared dx. After that, we integrate both sides. So integral dy is equal to integral 9x squared dx. The integral of a derivative of a function simply gives us back the function itself. So integral dy is equal to y equal to integral of 9x squared dx, which is 9x to the power of 3 divided by 3 plus c. Okay, this is the solution. So y is equal to 9 over 3, which is 3x3 plus the constant. And this is the neat representation. So dy equal 9x squared dx. As we said, we multiply the x to the right side. Then integral of dy, which is y, is equal to integral 9x squared dx equals 3x3 plus c. Verify that f of x equal to x5 plus ln x minus sin x is an antiderivative of f of x equal 10x4 plus 1 over x minus cosine x. Okay, what does that mean? We need to derive, okay, f of x to get lowercase f of x. So in other words, it means that f of x prime should give us what is seen below. Let us derivate, so it gives us 10. Why? Because 5 times 2 x4 plus derivative of ln x is equal to 1 over x. As a reminder, ln u prime is equal to u prime divided by u. And minus sin x, derivative of sin is cosine. So minus cosine x, because we have a minus on the outside. And this is the final answer as a verification and a proof. Module 3, definite integration. Now I understand that some parts may seem to have been replicated in other chapters, but still, this is mainly for the definite integration. At first, let's start with integral from 0 up to 2 of x dx. So it is equal to x squared over 2 between 2 and 0, which is equal to 2 squared over 2, which is 4 over 2, minus 0 equal 2. So x squared over 2 between 2 and 0, which is, by the way, can be written as f of 2 minus f of 0. 2 squared over 2 minus 0 squared over 2 equal 2. Constant function, evaluate integral between 5 and 1 of 4 dx. Now 4 is a constant, can be removed to the outside of the integral, and integral dx between 1 and 5 simply gives us x between 1 and 5, or 5 and 1. And you multiply it by 4. So we end up with 4x, and between 5 and 1, 4 can be multiplied from the outside, but anyway, so it is 20 minus 4, or 4 multiplied by 5 minus 1, the same thing, which is 4 times 4, or 16. Evaluate integral from 0 to 3 of 2x squared plus 1 dx. Straightforward. So it gives us 2x3 over 3 plus x between 3 and 0. So 2x3 over 3 plus x between 3 and 0, which is f of 3 minus f of 0. Meaning that first time we replace x by 3 minus replacing x by 0. Okay? So the enlarged format of that is 2 times 3 to the power of 3 over 3 plus 3, because we replaced x by 3, minus 2 times 0 to the power of 3 over 3 plus 0. Okay? And given that when you place 0 at the place of x, okay, you get nothing, you get 0. In our case, in this case, hence, this is equal to 2 multiplied by 3 to the power of 3, which is 9 by 3, or 27, divided by 3 plus 3. Okay? So it is 18 plus 3, or 21. Therefore, the answer is 21. Integral ex between 1 and 0. So it is equal to ex between 1 and 0 equal e minus 1, because e0 is 1. integral between pi over 2 and 0 of cosine x dx. So integral cosine x gives us sine x between pi over 2 and 0. Sine pi over 2 is equal to 1, and sine 0, 0. Let's check it out. So sin x between pi over 2 and 0, which is 1 minus 0, equal 1. This is why, because pi over 2 means it is the 90-degree angle over here. Okay, so this is the sine, which is the elevation on this circle. It is exactly equal to the radius in such case, which is 1. As for sine 0, meaning that for angle 0, sine, which is the elevation, the projection of caused by the angle on the y-axis, would be in such case 0. Why? Because you are exactly on the x-axis. That's why sine would be 0. Given integral between 4 and 1 f of x dx is equal to 7, find integral between 1 and 4 f of x dx. Now this one is a clever question. So integral between 4 and 1 f of x dx. At first, this is simply f, capital F, 4 minus capital F of 1, which is equal to 7 in our case. So what would be integral between 1 and 4? Integral between 1 and 4 f of x dx would be equal to f of 1 minus f of 4, which is the negation of this quantity here. So in such case, that would be equal to minus f4 minus f1, or minus 7. So the property being used is integral between b and a f of x dx is equal to minus integral between a and b f of x dx. And we obtain minus 7. Additivity property. Let's say integral between 0 and 2 f of x dx is equal to 5. And integral between 2 and 5, or 5 and 2, f of x dx is equal to 9. Find integral between 0 and 5. First of all, geometrically, so to speak, like if you consider a curve, the integral gives us the area between the curve and the x-axis. So let's say, or let's consider at first, integral between 0 and 2. This is between x equals 0, which is the origin, and x is equal 2, correct? This is the area between 0 and 2. This is the integral of f of x between these two boundaries. It gives us the area from x equals 0, asymptote, so to speak, or the line x equals 0, and x equal 2. Now, integral from 2 to 5 of f of x dx gives us the area of that same curve between 2 and 5. Let's consider 5 over here. Hence, integral from 0 to 5 is simply the sum of both areas, the one from 0 all the way to x equal 2, and from 2 to 5. So the property is the following. Integral from a to c f of x dx is equal to integral from a to b f of x dx plus integral from b to c f of x dx. Given that b is between a and c, so you can say that b belongs to the interval of a, c, or included, of course, or b is greater than equal to a, less than equal to c. Now, the first one, which is from 0 up to 2, is equal to 5, and from 2 to 5 equal 9. You add them both and you get 14. Find the area under f of x is equal to x squared from 0 up to x equal 2. Now, by the way, y equal x squared is the formula of the parabola, which is like this. Okay? From 0 up to 2. This is the area we're looking for. So the integral of x squared dx is equal to x3 over 3 between 2 and 0. So it is 8 divided by 3 square units. Net signed area. Evaluate integral from -1 to +1 of x dx. Now, there's a property about the odd functions, okay? So for an odd function, and when you have a symmetric interval, such as from -1 to +1, the integral would be 0. Why is that? Because if you plot y equal x from -1 to +1, it would look something like this. Now, the area that is negative below the x-axis is equal to that above the x-axis. So, positive area and negative area are equal to each other. Okay, so they cancel each other. Their sum is equal to 0. Just like a sine wave, by the way. Why is that? Because if you add the areas together, one is negative and the other quantity is positive, and they are equal to each other, so the integral or the overall area would be 0. Now, how do we identify an odd function? An odd function would respect the following criteria, which is f of minus x would be equal to minus f of x. So in our case here, f of minus x is equal to minus x, which is equal to minus f of x. Hence, this is an odd function. And we're going to prove that the integral would be equal to 0. So integral -1 to +1 of x dx is equal to x squared over 2 between 1 and -1 equal 1/2 minus 1/2, which is 0. So since f of x is equal to x is an odd function, the integral within a symmetric interval from -a to +a gives us 0. By the way, I forgot to mention that for an odd function, the function would be symmetric in respect of the origin of the axis. So whatever the function is doing in the first quadrant, that would be symmetric in behavior and in attitude, so to speak, like the curve and the direction would be symmetric to how the function is behaving in the third quadrant, which is this is the third quadrant. This is 1, 2, 3, and it is the fourth quadrant, in case you're wondering. As for an even function, for an even function, it would be symmetric in respect of the y-axis. For example, y is equal to x squared is an even function. Why? Because it is a parabola for whatever x to the right, okay, the same x to the right, x value, let's say it is 1 or 2, for 1 or -1, y would be the same value, okay? So, in other words, the function would be symmetric. It would be the mirror image of itself, okay, in respect of the y-axis. So, arithmetically, so to speak, f of minus x would be equal always to f plus x. So, for -1 or +1, which are two symmetric values in terms of the interval itself, f of 1 is equal to f minus 1, f of 2 is equal to f of minus 2, and etc. Now, for the parabola we have here, which is the equation y equal x squared, notice something. F of -1 is equal to f plus 1 equal x squared. Why? Because it is a square value. Okay? F minus 2 equal f plus 2, which is 4. Now, another characteristic we can notice with even functions is the fact that the same area that exists to the right of the y-axis is being reflected. It is the mirror image of the area to the left of the y-axis. In other words, technically, instead of evaluating the integral from minus 2 to plus 2 of x squared dx, which is actually the area from left to right between minus 2 and plus 2, the interval, we can simply convert that into integral from 0 to 2. We can evaluate the area to the right of the y-axis and multiply it by 2, given that the area to the right is equal to the area to the left. So you evaluate the area on one side and you multiply it by 2. This is how you get the answer. So integral from minus 2 to plus 2 x squared dx is equal to 2 multiplied by integral from 0 to 2 x squared dx, which is x3 over 3 between 2 and 0 multiplied by 2. Okay, so x3 over 3 between 2 and 0 is simply 2 to the power of 3, which is 8 over 3, multiplied by 2 on the outside, which is 16 over 3. Riemann sum approximation. Approximate integral from 0 up to 2 of x squared dx using a left Riemann sum with n equal 2. So here we need to divide the interval with n equal 2, meaning that 2 partitions, okay? And this is how you divide it. So 2 minus 0, which is the upper bound, minus the lower bound, divided by n. This is delta x. So delta x is equal to upper bound minus lower bound divided by n, which happens to be 2 also, equal to 1. After that, we multiply delta x with f of 0 and f of 1. We're going to see that. So the partition delta x is given by upper bound minus lower bound divided by n, with n equal to, which is 1. So the left endpoints are the following: x0 equals 0 and x1 equal 1. Lower bound and x1 equal 1. Hence, the left Riemann integral for n equal 2 would be 2 partitions, 2 divisions. Okay, the first one, now this is how you measure the integral, which is the area, correct? So here you have 2 divisions. So it is dx times f of 0, which is the area of this rectangle, and dx multiplied f of 1. Okay, so f of 1, let's say it is over here. Dx times f of 1 would be the area of this rectangle right next to it. So L2 is equal to f0. Of course, delta x doesn't change, so you can put it as a common multiplier, equal f0 plus f1 times delta x. f0 is x squared for x equals 0. So 0 squared plus f1 is 1 squared times delta x, which is 1. The accurate result for that integral is between 0 and 2 of x squared dx is equal to x3 divided by 3 between 2 and 0, which is 8 divided by 3, approximately 2.6 something. So of course it won't be that accurate. Again, let's approximate the same integral, but this time using a right Riemann sum, but still for n equal 2. Delta x is still equal to 2 minus 0, which is the upper and lower bound, divided by n, which is 2. equal 1. So for the right endpoints, these are x1 equal to 1 and x2 equal to, which is the upper bound. So R2 is equal to f1 plus f2 delta x. F of 1 is 1 square plus f of 2 is 2 square, which is 4, okay? So it is 1 square plus 2 square multiplied by delta x, which is 1, equal 5. Both of them are inaccurate, of course. Let's approximate now the same integral using the midpoint rule. So what is the midpoint? Okay, so between 0 and 2, the midpoints are, you have 1 in the middle, okay, but from 0 to 1, you have 0.5. And from 1 up to 2, you have 1.5. And these are the midpoints of the integral. So m2 is equal to f of 0.5 plus f 1.5 times delta x. Remember, delta x is 2 minus 0 divided by n, which is 1. So it is equal to 0.5 square plus 1.5 square multiplied by 1, which is 2.5. By the way, so far it might be the most accurate. To explain a little bit the difference between these three types so far. So at first, the left point rule states that you have f of 0, that would be the first point, then f of 1, okay, so 0 and 1. These are the rectangles, okay, by which we are approximating the area of the curve. So we've chosen 2 points to the left of the interval. Now, for the right point row, okay, the right side Riemann integral, that would be for f equal 1 and for f equal 2, okay? So this is the way that we are evaluating the integral. Now, for the midpoint, this is how the midpoint rule works. So you have the curve supposedly like this. This is the interval of 0, 1, 2, and this is the curve, for example. Okay, so we are choosing the middle point, and that would be like this, okay? So this is how, this is why actually it is the most accurate so far, okay? Because when we evaluate the area of this square here, you notice that this part is not actually part of the curve, it is outside of the curve. However, like, it is almost equal to this segment that is being discarded. Due to this equality, due to this approximation, it is so close to the actual area of the curve. Why? Because the part that is left out here, which is this part, is approximately equal to the part that is being added here to this square, okay, to the rectangle area. Same thing on the right side, okay, we're choosing this point as the height of the rectangle. So this part that is included here within this rectangle that for which we're measuring the area, okay, this part is almost equal to the part that is actually within the curve domain, okay? And this one here is not, like, it is outside of the curve. However, it makes up for the part that is being discarded. Trapezoidal rule. Okay, what is this rule about? You see, this time when we are evaluating the area, instead of taking or calculating the area of a rectangle, we are calculating the area of the trapezoid, meaning that you have here different heights, correct? For example, let's say you have a point here and a point here. Now, instead of measuring the area of the rectangle, which leaves out a large chunk or adds up a large chunk to the curve, here you are taking a line and this becomes a trapezoid, okay? It's no longer a rectangle, it becomes a trapezoid. So again, in a magnified way, instead of getting the area of a rectangle here, you're getting the area of the trapezoid from this point to this point, which would be much accurate. Why? Because in the area of the rectangle, let me change the color. In the green, you have left out a major part of the curve. It's being discarded. However, when you consider the trapezoid, it's more accurate. Why? Because we've added this part. It's no longer this one. You have a large chunk that was missing before that is added right now to the area calculation. So how to evaluate this integral? Suppose the curve is like this and it is stretching from interval between 0, 1 all the way up to 2. Okay? So we have two trapezoids. This is how we're dividing the area. The first one is from 0 to 1. Okay? So how to evaluate this area from 0 to 1? It is simply the height of the first side, which is f of 0, plus the height of the second side, or f of 1, divided by 2, times delta x. That would be the area of the first trapezoid. Plus the first side here, which is f of 1, plus the second side, which is f of 2, divided by 2 times delta x. This is why you have 2f1 over here, because it's mentioned twice. So delta x over 2 can be removed to the outside as a common multiplier. You end up with delta x over 2 multiplied by f0 plus 2f1, because f1 is occurring twice, plus f2, again, all of that multiplied by delta x divided by 2. So let's clean it up. You have delta x over 2. Delta x is 1 already over 2 times f of 0 is the value of f for x equals 0. So it is 0 square plus 2 f1. f1 is 1 square plus f of 2. You replace 2 in x squared, you get 2 square, which is 4, equal to 6 over 2, which is 3. Close to the correct or the accurate answer, okay, but in this case, the midpoint has performed a little bit better. Mean value of a function. What is the mean value? Okay, let's say you have discrete points or discrete values, suggesting like you have 1, 3, 2, 1. What would be the mean value for these samples, so to speak? It would be the sum of these different values divided by 4, which is the number of samples. So this is equal to 3 plus 2, 5, 6, 7 divided by 4. However, how to get the average value of a sum of a function on 0, 3? So let's get the average value. This is actually would be integral from 0 to 3, which is the upper and lower, or lower to upper bound of the function f of x dx, and we divide that by the length of the interval. In such case, that would be the upper bound minus the lower bound. 3 minus 0. Just like in discrete points, you get the sum of all values divided by the number of samples. Here, we don't have discrete values, we have an interval. So you divide by the length of the interval. Hence, f average is equal to 1 divided by b minus a. This is the formula, by the way. Integral from a to b f of x dx. Equal to 1 divided by 3 minus 0, which is 3. Integral from 0, the lower bound, up to 3, upper bound, of x squared dx. Equal 1/3 times x3 over 3 between 3 and 0, which is 3 to the power of 3, or 27, divided by 3, multiplied by 1/3. 27 over 3 is 9. So 9 over 3, which is 3. Analytically, for y equal x squared, that would be the plot of the function for, like, okay, 1, 2, 3. F of 1 is equal to 1. F of 2 is equal to 4. 3, 4. And f of 3 would be equal to 9, okay? 5, 6, okay, all the way up. So it would be something like that. The midpoint, not the midpoint, like the average value would be 1, 2, 3. Approximately, that would be the average value in the interval from 0 to 3, which makes sense, by the way, because you see it in the middle of the altitude. Integral inequality. Suppose f of x is greater than equal to 2, less than or equal to 5. So the function f of x has a height bounded by 2 as the lowest point and 5 as the highest point. You can imagine it as an airplane moving between 2,000 feet altitude and 5,000 feet. It is bounded between these two altitudes. Okay, so its height or altitude can be greater than or equal to 2,000 feet, less than equal to 5,000. For all x between 1 and 4, 1 and 4 would be the interval, like the horizontal distance. Okay, at the first, like from 1,000 miles from the airport, let's say, to up to 4,000 miles, 1,000 and 4,000, or 1 or 4, 1 and 4 being included within the closed interval. So it is a closed interval. Find bounds for integral from 1 to 4 f of x dx. At first, the simplest thing to do is, since you have an integral from 1 to 4 f of x dx, okay, let's change this inequality by inserting the integral from left to right. Okay, so since f of x is greater than or equal to 2, less than equal to 5, hence integral of 2 dx between 1 and 4 is less than or equal to integral 1 to 4 f of x dx, less than equal to integral from 1 to 4 of 5 dx. This gives us, okay, 2x between 4 and 1, less than equal to integral from 1 to 4 f of x dx, less than or equal to 5x between 4 and 1. So it is 2 multiplied by 4 minus 1, less than or equal to integral from 1 to 4 f of x dx, less than equal to 5 times 4 minus 1. So to the left, 4 minus 1 is 3 times 2, 6. less than or equal to integral from 1 to 4 f of x dx less than equal to 5 times 3, which is 15. Let's check it out. So you simply integrate from left to right. Correct. Okay, integral of 2 dx between 1 and 4 gives us 6. To the right, integral of 5 dx between 1 and 4 gives us 5x between 4 and 1. Okay, so it is 5 times 4 minus 1, which is 15. Hence, these are the bounds of the integral. Definite integral of a rational function. This should be straightforward. So integral between 1 and e of 1 over x dx, which can be written also as integral between 1 and e dx over x, which is du over u. It gives us ln u plus c if it was indefinite. Here in this case, you get ln x, an absolute value between e and 1. Let's check it out. So integral 1 over x dx is equal to ln x between e and 1 equal ln e minus ln 1. By the way, log 1 is equal to 0 and ln e is equal to 1. Hence, the answer is 1. And this is why. Because this is the plot of the logarithm. You see, the logarithm or log, as x approaches 0, it approaches minus infinity. And by the way, the domain of definition is between 0 plus all the way to plus infinity, meaning that it's not defined for x being negative. Then at x equal 1, it clips the x-axis, meaning it becomes 0. For x equal e, that would be around, actually e won't be here. It is around 2.7 something, okay? ln e is equal to 1. This is why they called it e, because it's a characteristic value. Then it keeps growing all the way to plus infinity. So finally, the answer of that integral is 1. Integral from 0 to 2 of 3x squared plus 2x plus 1 dx. This is straightforward. It is equal to 3x3 divided by 3 plus 2x squared over 2 plus x plus c. But here we have a definite integral, so we have two bounds. So it is equal to 3x3 over 3, which is x3, plus 2x squared over 2, also factored out, which is x squared, plus x, between 2 and 0, which gives us 8 plus 4 plus 2, minus 0, which is 14. Integral from 0 to pi, and from pi up to 2 pi of sine x dx. For the first one, okay, integral sin x gives us minus cosine x between pi and 0, which is cosine pi is minus 1, minus minus plus 1, minus cosine, okay, minus cosine 0, which is minus minus 1 equal to. I hope it did not confuse you, but let's explain it further in the second example. Between pi and 2 pi sin x dx, okay, integral between pi to pi sin x dx is equal to minus cosine x between 2 pi and pi. 2 pi means cosine 0. It's the same thing, because with 2 pi after this rotation, you get back to 0.0. So minus cosine 2 pi, which is minus cosine 0 or minus 1, minus f of pi, which is minus cosine pi, correct? minus cosine pi. Now, remember, cosine pi is minus 1. It is on the second quadrant. Minus 1, okay, minus 1 times minus gives us plus 1. And you have a minus, another minus on the outside. So the final answer is minus 2. The same concept applies for all integrals. Using the definition of the definite integral, evaluate integral from 0 to 1 x dx. So what is the definition? Actually, first we divide the entire interval to n partitions. So from 0 to 1, you have 1 over n partitions. That would be delta x, which is the step. The step is always constant. That would be multiplied by the height of the function at each point. Now, for each point, that would be f of xi, or x at an I point, with the fxi is equal to, meaning that would be f of I over n. Okay, this would be f of I divided by n. Hence, we'll check the following solution. Okay, so partition from 0 to 1 into n equal parts. That would be, again, delta x equal 1 over n. Now, the right endpoints, xi is equal to I over n, with I going from 1 all the way to n as a sum. The Riemann sum is given by sigma I equal 1 to n fxi times delta x for an infinitesimal rectangle, or a rectangle with a very small base. That would give us an accurate value. So sigma I equal 1 to n fxi delta x is equal to sigma from I equal 1 to n of I over n times 1 over n, which is 1 over n squared sigma I equal 1 to n of I. At first, we partitioned the interval into n equal divisions, correct? So delta x is equal to the upper bound, which is 1 in this case, minus the lower bound, which is 0, divided by n, or 1 over n. Now, we need to also use the right endpoints, meaning that delta x is a constant step, horizontal step, that would be multiplied by the height of the function to get the area of the rectangle at each point. And the sum of these areas would give you the area of the curve, or between the curve and the x-axis. So the right endpoints are given by xi is equal to I, which is the value stepping from 1 all the way to n, divided by n, which is the number of subdivisions. So the Riemann sum is given by sigma I equal 1 to n fxi delta x. What is fxi? With xi, of course, being I over n. fxi, you simply replace x here, which is the function of f of x, with I over n. Multiplied, so it is the sigma from I equal 1 to n of I over n. This is fxi, multiplied by the number of partitions, which is 1 over n, the number of subdivisions. It gives you 1 over n squared. You can move it to the outside, sigma from I equal 1 to n of I. This sum here has a formula, which is sigma of I from I equal 1 to n is equal to n times n plus 1 divided by 2. It's a conventional formula. So we obtain 1 over n squared multiplied by n times n plus 1 over 2, which is the answer for sigma of I from I equal 1 all the way to n. You can factor out n, so you end up with n plus 1 divided by 2n. Let's take the limit for n approaches infinity. This would give you Okay, so we can break it down to simplify it for you. Limit n approaching infinity of n over 2n plus 1 over 2n, which is 1 half plus 1 over 2n. As n approaches infinity, 1 over 2n approaches 0, so we end up with 1 over 2. That would be the area of the curve, 1 half. Evaluate a definite integral using the fundamental theorem of calculus, which is the classical way of solving the integral anyway. So integral from 0 to 3 of 2x dx is simply 2x squared over 2, which is x squared between 3 and 0 equal f of 3 minus f of 0, which is 9. So it is f of 3 minus f of 0 equals 3 squared minus 0 squared, or 9. Same example here. So x3 over 3 between 4 and 1. As simple as that, which is 4 to the power of 3 divided by 3 minus 1/3, 21. Integral from 0 to pi over 2 of sin x dx. So integral sin x dx gives us minus cosine x, and between pi over 2 and 0, okay, so cosine pi over 2 is 0, definitely, minus cosine of 0, which is 1. So 1, you have minus here and minus here, so plus 1. Okay, 0 minus minus 1 plus 1. Let f of x be equal to integral from 0 to x d3 dt. Find f prime x. Now, despite the fact that it seems a little bit complicated, since we're saying f prime of x, you can simply say, okay, this is the derivative of the integral from 0 to x d3 dt. Derivative of the integral would give you the internal function immediately, and in function of x, okay, that would be a function of x, so x3. Or, to prove it to you, so f prime of x is equal to the derivative of integral from 0 to x d3 dt. So we solve the integral at first, which gives us t4 divided by 4 between x and 0, which is equal to x4 over 4. And let's get the derivative for that. This is 4x3 divided by 4, which is x3. So we've gotten the same result. So in short, f prime of x is equal to f of x, which is x3. Straightforward. Another similar example, f of x is equal to integral from 2 to x, t squared plus 1 dt. So f prime of x is equal to x squared plus 1. You simply place this function, which is the internal function of the integral, and you swap t with x. As simple as that. So it is equal to x squared plus 1. Also here, f prime of x is equal to sin x. Okay, so from 1 to x sin t dt, f prime of x equals sin x. Chain rule with FTC. By the way, FTC stands for the fundamental theorem of calculus. So how do we get here f prime of x? At first, f prime of x is equal to the derivative of the integral between 0 and x2 cosine t dt prime. Let's solve the integral. This gives us integral of cosine gives us sine of t between x squared and 0 equal sin x squared prime minus 0, of course, 0 doesn't matter. Sin x squared, okay, the derivative for that, you see, this is a compounded function, meaning that you have the sin and a function within the sin for which the derivative is no longer 1. So, based on the chain rule, derivative for sin x squared is equal to x squared prime, derivative for the inner function, multiplied by the cosine, or the sin x squared prime, okay? So it is derivative of the inner function, the nested function, times the derivative of the function as a whole, which is x squared prime is equal to x, derivative of the inner function of the sine, then derivative of the sine itself, which is cosine, and you leave the internal, of course, which is x squared. So let's check it out. F prime of x is equal to cosine x squared times the derivative of x squared over the x, which is 2x cosine x squared. This is the difference between what we've seen so far and this one. Another chain rule example, let f of x is equal to integral from 1 to 3x d4 dt. Find f prime of x. At first, we simply replace t by 3x. Okay, so that would be 3x to the power of 4 times the derivative of 3x in respect of x. Let's check it out. So f prime of x is equal to 3x to the power of 4 times derivative of 3x is simply 3, which gives us, okay, 3 to the power of 4, 81 times 3 times x4, or 243x to the power of 4. Let f of x be equal to integral between 5 and x of t squared dt. Find f prime of x. So the formula is d over dx of integral between a and x. However, x here is the lower bound, not the upper bound, of f of t dt. In such case, it would be equal to minus f of x. Hence, f prime of x is equal to minus x squared. Let's try to solve it in the classical way, so to speak. So, f prime of x is the derivative of the integral between 5 and x of t squared dt. Let's find the integral at first. So this is equal to t to the power of 3 divided by 3 between 5 and x. And once we get the final answer, we derive in respect of x, which is equal to 5 to the power of 3 divided by 3 minus x3 divided by 3. Prime, let's find the derivative. So we know that the derivative of every constant is equal to 0. So the first part becomes 0 minus 3x squared over 3, which is equal to minus x squared. This is how we came up with the formula that the derivative in respect of x between a and x ft dt is equal to minus f of x. Net area. Evaluate integral between minus 1 and plus 1 x3 dx. At first, we need to notice something, that we have a symmetric interval, symmetric in respect of 0, of x equals 0. Let's find out if the function is an odd function, which means that it is symmetric in respect of the origin. An odd function has the following property: f minus x is equal to minus f of x. So f minus x is equal to minus x3, which is equal to f of x also. Hence, this function is an odd function symmetric to the origin. So automatically, the integral here is equal to 0. Why? Because you have a positive area equal as the negative area. When we add them together, it amounts to 0. Now, let's solve it classically. So this is x4 divided by 4, okay, between 1 and minus 1, which is 1 over 4 minus 1 over 4 equal 0. Therefore, and we can deduce that simply by saying that x3 being an odd function, and we are evaluating the area on a symmetric interval between minus 1 and plus 1, hence the answer is 0. The same thing here for x, which is, by the way, the first bisectrous. It has this following graph, symmetric to the origin. Actually, let's clean it up. So f of minus x is equal to minus f of x. Hence, it is an odd function. So the area here is also 0. Evaluating a definite integral. Evaluate integral from 0 to 2. We've seen a lot of these examples already. So the answer is 3x3 over 3 plus 2x between 2 and 0. Okay, 3x3 over 3. So x3 plus 2x for x equal 2, which gives us 8 plus 4 or 12. So it is equal to 12. Given f of x is equal to integral between 0 and x of 2t plus 1 dt, find f of 3. So simple. So first, let's solve the integral. It is equal to t squared over 2 plus t between x and 0, which is t squared plus t between x and 0, or x squared plus x. F of 3 is equal, then you simply replace x by 3 squared plus 3, which is 9, 10, 11, 12. Should also give us 12. And this is the neat solution. So it is t squared plus t between 3 and 0. You replace, or you plug 3 as the replacement of t. You get 3 squared plus 3 minus 0 equal 12. Let f of x be equal to integral between sin x and 0 of square root of 1 plus t squared dt. Now, okay, so f prime of x would be equal to the inner function, the square root of 1 plus t squared, as we replace t by sin x, which is square root of 1 plus sin squared x multiplied by the derivative of sin x in respect of x, which is equal to square root of 1 plus sin squared x times cosine x. Let's check it out. So the fundamental theorem of calculus and the chain rule gives us f prime of x is equal to square root of 1 plus sin squared x times cosine x. And this is the final answer. Cosine x, square root of 1 plus sine squared x. Evaluate integral from 2 to 1 of 1 over x squared dx. It seems a little bit challenging. However, if you look at it, this can be written as integral from 1 up to 2 of x to the power of minus 2. You simply move it from the denominator to the numerator and you flip the sign of the power of x dx. So going back to the main formula, integral xn dx is equal to x to the power of n plus 1 divided by n plus 1 plus c if it was unbounded. So here it is equal to x minus 2 plus 1 divided by minus 2 plus 1 between 2 and 1. So x to the power of minus 1 is simply 1 over x, and minus 2 plus 1 is minus 1 in the denominator, so it is minus 1 over x between 2 and 1. Hence, it is equal to minus 1 over x. Okay, this is minus here. Between 2 and 1 equal minus 1 half minus minus plus 1, which is 1 over 2. And there you go. So it is minus 1 over x between 2 and 1, which is minus 1 half, minus minus 1, so plus 1 minus 1 half equal 1 half. F of x is equal to integral between x3 and 0 of et dt. Find f prime of x, so f prime of x is equal, again, to e to the power of t, the inner function, with t equal to x3, multiplied by the derivative of x3 in respect of x. So it is equal to 3x squared ex3. Let's check it out. Correct. So ex3, derivative of x3 in respect of x, is equal to 3x squared ex3. Let g of x be equal to integral from x3 to x2 of 1 plus t squared dt. So the formula is for g prime of x is equal to f of x3 multiplied by the derivative of x3 in respect of x minus, because remember, it is like an integral between b and a, ft dt, for example, is equal to fb minus f of a. So fx3 times dx3 over dx minus fx squared times dx squared over dx, derivative of x squared in respect of dx. Using the generalized Leibniz rule, derivative in respect of x of integral between vx and ux ft dt is equal to f of v of x times v prime of x minus f of u of x times u prime of x. F of t is equal to 1 plus t squared. F of vx, you simply replace x3 in t, correct? So that would be x3 to the power of 2. And fx squared is equal then to 1 plus x to the power of 4. You replace t by x squared. Hence, g prime of x is equal to the following. Okay, f of v of x, which is v of x is equal to x3. U of x is equal to x squared. Fv of x is equal to 1 plus x3 to the power of 2, which is x9, multiplied by v prime of x, which is 3x squared, minus f of u of x, which is 1, plus, replace like we replace t by x squared, you get x4, multiplied by du of x, which is 2x. So we end up with, correct, 1 plus x6, 3x squared, minus 1 plus x4, 2x. After that, we simply develop what we've gotten from the previous answer. So we end up with 3x8 minus 2x5 plus 3x squared minus 2x. Chapter 5, U-SUBSTITUTION. So let's evaluate integral of 2x times x squared plus 1 to the power of 5 dx. How to solve this one? First, we suppose that u is equal to x squared plus 1. So du in respect of x, which is du over dx, would be 2x. And notice something, this is 2x over here. Hence, du, okay, multiply the x to the right, so you end up with du is equal to x dx. So let's replace them within the integral. This is equal to integral of 2x dx is du multiplied by x squared plus 1 is u, which is elevated to the power of 5, by the way, equal integral of u5 du or u6 over 6 plus c. Again, we restore the original value of u, so that would be x squared plus 1 to the power of 6 over 6 plus c. Another name for the U-substitution is the change of variables. So again, let u be equal to x squared plus 1 du equal to x dx, hence you end up with integral of u5 du. which resolves into u to the power of 6 divided by 6 plus c. Then you restore the original value of u, which is x squared plus 1, to the power of 6 over 6 plus c. Another example, integral of 3x squared plus x3 plus 4 to the power of 7 dx. Let u be equal to x3 plus 4. Then du is equal to 3x squared dx. So this ends up being integral 3x squared dx is du multiplied by u to the power of 7. Same method. So du 3x squared dx, u equal x3 plus 4, integral u7 du is equal to u8 over 8 plus c, which is x3 plus 4 to the power of 8 divided by 8 plus c. Exponential substitution. Evaluate integral of e 5x dx. Let's suppose that u is equal to 5x. Then du would be equal to 5 dx, or in other words, du over dx equal to 5, hence du equal 5 dx. So this would become integral of eu, okay, times, okay, so du is equal to 5 dx. So we need to replace dx by du. E 5x is eu, okay. So since du is equal to 5 dx, hence dx would become du over 5. So times du over 5. 5 is a constant, can be removed to the outside of the integral. So 1 over 5 integral eu du, which is equal to eu over 5, or e 5x over 5 plus c. And this is the full solution. U equal 5x, du equal 5 dx, dx equal du over 5. You place it back in the integral, so you end up with 1 over 5 integral eu du equal to 1 over 5 eu plus c, or 1 over 5 e5x plus c, because we reinstated the original value of u. Logarithmic form. Integral of 4x over x squared plus 9 dx. Now, this method doesn't always work, but here clearly it happens that we have the derivative of the denominator in the numerator, and we're going to see it. So if we suppose that u is equal to x squared plus 9, then du is equal to x dx. Okay, so x dx is simply equal to du over 2, correct? Let's place it back in the equation. So integral of 4 times x dx, which is 4 times du over 2, divided by u, which is x squared plus 9. Okay, so this is 4 over 2, which means it is du, integral du over u, equal 2 times ln u plus c, or 2 ln x squared plus 9 plus a constant. Let's check it out. So u equal x squared plus 9, du equal 2x dx, 4x dx equal 2 du, okay? Another way to go about it, you simply multiply both sides by 2 to get the form that we have in the numerator, which is 4x dx. Okay, so 4x dx equal 2 du divided by u, so equal to integral 1 over u du, or 2 ln u plus c. This is the final answer. Trigonometric substitution. So u equal 7x for integral sin 7x dx, then du is equal to 7 dx. So dx is equal to du over 7, hence integral of sin u du over 7, you remove the 7 to the outside, which is 1/7 times minus cosine u plus c, equal to minus 1, 7 cosine 7x plus a constant. U equals 7x, du equals 7 dx, dx equal du over 7, so equal 1 over 7 integral sin u du, and you end up with minus 1 over 7 cosine 7x plus c. Same thing, integral cosine 4x minus 3 dx, so u is equal to 4x minus 3, du is equal to 4 dx. Hence, dx equal du over 4. So you replace dx with du over 4 times cosine u, and you integrate. So it is 1 over 4 integral of cosine u du, which is equal to 1/4 sin u plus c. Then you reinstate the original value of u, which is 4x minus 3, hence 1/4 sin 4x minus 3 plus c. Evaluate integral of x dx divided by x squared plus 1. So let's say u is equal to x squared plus 1, du equal to x dx. So x dx is equal du over 2. So you end up with, and this in the denominator is u, so it is integral of du over u multiplied by 1/2 equal 1/2 ln u plus c. So u equal x squared plus 1, du is equal to x dx, correct? So x dx is equal to 1/2 du. You place it back in the equation. So it is 1/2 integral of du over u, which is 1/2 ln u plus c, with u equal x squared plus 1. So it is 1/2 ln x squared plus 1 plus c. Radical function. Integral of x, square root of x squared plus 4 dx. So let's suppose that u is equal to x squared plus 4. Then du is equal to x dx. Hence, x dx is equal du over 2. That's the first step. Now, let's place them back within the integral. So it gives us integral x dx is equal du over 2 times square root of x squared plus 4, which is u, equal to 1/2, we remove it to the outside, square root of u du. Note that square root of u is simply u to the power of 1/2. So its integral gives us u to the power of 1/2 plus 1 divided by 1/2 plus 1, which is u to the power of 3 over 2 divided by 3 over 2, or 2/3 u square root of u. As simple as that. Let's place them back. Okay, so it is 1/2 times 2 over 3 of u square root of u plus c. So u equal x squared plus 4, du equal to x dx. Hence, x dx is equal to 1/2 du. Then 1/2 integral, okay, so 1/2 du, you place it here. This is 1/2 integral u to the power of 1 over 2 du, which is 1/2 times 3 over 2, which is 2/3, multiplied by u to the power of 3 over 2 plus c, which is 2 factors out because it ends up being 2/3 times 1 over 2 u to the power of 3 over 2 plus c, which is u to the power of 3 over 2, as a reminder, is u to the power of 1/2 times u, correct? Because it is 1/2 plus 1. So it is u square root of u, which is 1/3 of u to the power of 3 over 2 plus c. We reinstate the original value of u, which is x squared plus 4. So this is the final answer. Definite integral with substitution. Evaluate the following integral. So here we have upper and lower bounds. It's no longer an indefinite integral. of 2x, x squared plus 1 to the power of 3 dx. So what does change in such case? Let's say u is equal to x squared plus 1, du is equal to 2x dx, okay, which is this part, 2x and dx. Now, since x is changing between 0 and 1, for x equals 0, okay, since we transferred from dx to du, correct? So for x equals 0, u, which is equal to x squared plus 1, becomes 1, which is 0 squared plus 1. For x equal 1, then u becomes 1 squared plus 1 or 2. So the bounds themselves have changed. So u equal x squared plus 1, du equal 2x dx. For x equals 0, u is equal to 1. X equal 1, u equal 2. Then the integral becomes the following. Lower bound, which was 0 in respect of x, becomes 1 in respect of u. The upper one becomes 2. Then 2x dx is du times x squared plus 1, which is u to the power of 3. Let's solve it. This is u to the power of 4 over 4 between 2 and 1, which is 2 to the power of 4 over 4, or 16 over 4, minus 1 over 4, or 15 over 4. By the way, you can simply solve the integral, then reinstate. Okay, so after we've gotten u4 over 4 as a result, you can reinstate the value of u as being x squared plus 1 to the power of 4 divided by 4, and then you get the value in respect of x equal 1 as upper bound and x equals 0 as lower bound. But if you choose to keep it as u, we need to follow the u values, not the x values, in respect of upper and lower bounds. Definite integral between 0 and 2 of e3x dx. So u equal 3x, then du equal 3 dx. So dx is equal to du over 3. Now, for the upper and lower bounds, for x equal 0, then u, which is equal to 3x, becomes 0, actually stays 0. For x equal to u, which is 3x, becomes 6. So it is integral between 0 and 6 of eu, and the x is du over 3. You remove 3 to the outside, it is 1/3 integral of eu du between 0 and 6 equal 1/3 eu from 6 to 0 equal 1/3 e6 minus e0, which is 1. That's the final solution. So u equals 3x, du equals 3 dx. U is between 0 and 6, as we mentioned. It becomes 1/3 integral from 0 to 6 eu du, which is 1/3 e to the power of 6 minus 1. Tangent function, evaluate integral of secant square 5x dx. So u equal 5x. Then du over dx is equal to 5, or du equal 5 dx. We replace it back in the equation with u equal 5x, so it is integral of secant square of u times dx equal du over 5. You remove 1 over 5 to the outside of the integral. Secant square u du, which is 1/5, tan u, which is tangent of 5x plus c. Let's check it out. U equal 5x, du equal 5 dx, so it is 1/5 of integral secant square u du. Integral secant square u du, based on the trigonometric functions, this is how I know that, is equal to tan u. So you obtain 1 over 5, then 5x plus c. Integral of 1 over 3x plus 1 dx. Straightforward, u equals 3x plus 1, du equals 3. So let's check it out. U equals 3x plus 1, du equals 3 dx, hence dx equal du over 3. So it is integral of du over u multiplied by 1/3 from the outside equal 1/3 ln u plus c with u equal 3x plus 1. High power composition, u equal x squared plus 5, du equal to x dx. So x dx equal du over 2. You end up with integral of u to the power of 8 times x dx, which is du over 2. So equal 1/2 integral u8 du, which is u9 over 9 times 1/2. So 1 over 18 u9. Let's check it out. U equal x squared plus 5 du equal to x dx. So x dx equal du over 2. Place it back within the equation. Integral of u du multiplied by 1/2 from the outside, it is 1/2 times u9 over 9 plus c, which is u9 over 18. And again, u is x squared plus 5. You reinstate the original value for u plus c. Sine squared structure. Integral of sine x cosine to the power of 5x dx. So let's say u is equal to cosine x. Du is equal to minus sine x dx. So sine x dx is equal to minus du. Now, this is sine x dx. You replace it with minus du, minus to the outside. You remove it outside of the integral of du multiplied by cosine x to the power of 5 is u to the power of 5. So it is integral minus integral u5 du, which is minus u6 over 6 plus c. Then you reinstate the original value of u, which is cosine x. Let's check it out. U equal cosine x, du equal minus sine x dx. Hence, it is minus integral of u5 du, because sine x dx is replaced by minus du, and cosine 5x by u to the power of 5. Hence, it is minus u6 over 6 plus c, as we mentioned, which is minus cosine to the power of 6x over 6 plus c. Evaluate integral of ex squared times 2x dx. Again, let's suppose u is equal to x squared, which is the power of the exponential. Then du is equal to x dx. Notice that we already have that within the equation. So you simply swap 2x dx by du. You end up with integral of eu du, which gives us eu plus c as the final answer. Let's check it out. U equal x squared, du equal to x dx. You simply replace it within the equation immediately. You end up with integral eu du equal eu plus c. Evaluate integral between 0 and pi over 2 sin x cosine 3x dx. So u equal cosine x, du is equal to minus sine x dx. So sine x dx, which is this part, is equal to minus du. You can replace them immediately. You end up with integral from 0 to pi over 2. Sine x dx is minus du multiplied by cosine to the power of 3 of x, which is u to the power of 3, equal to u4 over 4 minus on the outside between pi over 2 and 0. Actually, I kept pi over 2 and 0 as values because I'm going to reinstate the original value for u, which is equal to minus, what is u? It is cosine x to the power of 4 divided by 4 between pi over 2 and 0. Now, his method was to keep u and to change the values of x boundaries into u boundaries. So u equal cosine x du equal minus sine x dx. For x equals 0, u, which is cosine 0, becomes 1. Remember, u is equal to cosine x. For x equal pi over 2, u becomes 0, which is cosine pi over 2. So minus integral between 0 and 1, u3 du, which is, you can flip them. It is plus integral between 1 and 0, u3 du, which is u4 over 4 between 1 and 0, equal 1 over 4. Integral of 6x divided by x squared plus 7 dx. Let u be equal to x squared plus 7. Then du becomes 2x dx. Now notice something. If we multiply by 3 on both sides, to the left and to the right of the equality, you end up with 3 du is equal to 6x dx. So we can swap 6x dx with 3 du immediately. So integral of 3 du divided by u, which is x squared plus 7. You move 3 to the outside of the integral, equal 3 ln u plus c, with u equal to x squared plus 7. So 3 ln x squared plus 7 plus c. u equal x squared plus 7, du equal 2x dx, 6x dx equals 3 du. The same thing that we talked about, which is 3 integral of 1 over u du equals 3 ln u, which is ln x squared plus 7 plus c. Integral of 4x3 plus 2 times e x4 plus 2x. So let's say u is equal to x4 plus 2x. Then du is equal to 4x3 plus 2 dx. You notice 4x3 plus 2 and dx. So this is du. This is equal to integral of eu du, which is equal to eu plus c, or e x4 plus 2x plus c. So u is equal to x4 plus 2x, du equal 4x3 plus 2 dx, which is this part. Hence, integral eu du equal eu plus c, or e to the power of x4 plus 2x plus c. Integral of x divided by square root of x squared plus 9 dx. So let's suppose u is equal to x squared plus 9. Then du is equal to 2x dx. So x dx is equal to du divided by 2. Let's replace each term. X dx is equal to du over 2 divided by square root of u. So it is 1/2 integral du over square root of u. You move it to the upper side of the integral. So it is 1/2 integral of u to the power of minus 1/2 du equal 1/2 u to the power of minus 1 over 2 plus 1 divided minus 1 over 2 plus 1, which is 2, 1/2 times 2 times square root of u. It should be square root of u plus c. Let's check it out. So u equal x squared plus 9, du equal to x dx. X dx is equal to 1/2 du. You place it back within the equation, we end up with 1/2 du. 1/2 is taken to the outside. Integral of 1 over square root of u, which is u to the power of minus 1/2. You move it from the denominator to the numerator and you flip the sign, which is 1/2 u to the power of minus 1/2 plus 1 over minus 1/2 plus 1 equal u to the power of 1 over 2 plus c, which is square root of x squared plus 9 plus c. Integral from 0 to 1 x times x squared plus 2 to the power of 4 dx. Let u be equal to x squared plus 2. Then du equal 2x dx. In other words, du over 2 would be equal to x dx. So we replace x dx with du over 2. You end up with integral from 0 to 1 du over 2 times u to the power of 4, given that u is equal to x squared plus 2. So we move 1/2 to the outside and integral from 0 to 1. Okay, now 0 and 1 need to be changed. Okay, so u4 du, 0 and 1 pertain to x. However, u is equal to x squared plus 2 is now the new variable. So for x equals 0, which is the lower bound, u is equal to. For x equal 1, then u equal to x squared plus 2, which is 3. Hence, the new bounds or boundaries are the following. From u equal 2 to u equal 3. So u equal x squared plus 2, du equal 2x dx. You place them back within the equation. X dx equal 1/2 du. Now, also changing the boundaries. So for x equals 0, u equal x squared plus 2 is equal to. For x equal 1, u equal 3. Hence, it is 1/2. So this integral becomes 1/2 integral from 2 to 3, u4 du, which is 1/2 u5 over 5 between 3 and 2. Equal to u5 over 5. Okay, for u equal 3, that would be 3 to the power of 5 divided by 5 minus 2 to the power of 5 divided by 5. So 1 over 10, 243 minus 32, which is 211 divided by 10. Module 6, integration by parts. This is the formula. So integral of u dv is equal to uv minus integral of v du. So let's suppose u is equal to x, then du is equal to 1 dx. dv is equal to ex, then v is equal to integral ex dx, which is also ex. We leave the constant to the end of the solution. Hence, integral of u dv, with u being x, dv ex dx, okay, gives us u times v, which is x ex minus integral of v du, which is ex dx, equal x ex minus ex, or ex times x minus 1 plus c. Again, integral u dv is equal to uv minus integral v du, with u equal x, then du equal dx, dv equal ex, v is equal to ex. So integral of u dv is equal to u times v, which is x ex, minus integral of v du. This is v times du, which is x ex dx, which gives us x ex minus ex plus c, or ex times x minus 1 plus c. Evaluate integral of ln x dx. So let's say u is equal to ln x, du is equal to 1 over x dx. Don't forget the final part, okay? Because it is du over dx, which is 1 over x. dv is equal to dx. Then v is equal to integral dx, which is equal to x plus c. We leave the constant till the end. So this is integral of u dv, with u being ln x and dv equal dx. The solution is equal to uv minus integral of v du. Let's fill in the blanks. So u v, which is ln x times x, or x ln x, minus integral of v du, which is x times 1 over x dx. This is v du. You cancel out x, so we are left with x ln x minus x plus c. And this is the clarified solution. U equal ln x and dv equal dx. Du equal 1 over x dx. V is equal to x. You fill it within the integral. You end up with x ln x minus x plus c. Integral of x sin x dx. Let's suppose u is equal to x. Du equal dx times 1, which is dx. dv equal sin x, hence v equal integral sin x dx equal minus cosine x. U equal x again, du equal dx, dv equal sin x, then v equal integral of sin x dx, or minus cosine x. Integral of u dv is equal to u times v, which is x times minus cosine x, or minus x cosine x, minus integral of v du, which is minus integral of minus cosine x dx, gives us, okay, plus sine x plus c. Hence, the final answer is minus x cosine x plus sin x plus c. Similar one, integral x cosine x dx. Let's say u equal x, du equal dx, dv equal cosine x, then v equal integral cosine x dx, which is sine x. So integral u dv is equal to u times v, or x sine x, minus integral of v du, which is minus integral sin x dx, which gives us x sin x plus cosine x plus c. Another one, integral ex sin x dx. Now, in order to choose u and dv, u is usually picked in a way that when you get the derivative of u, you would get to eliminate its value. For example, for x, du would be 1 dx, okay? So we need to intelligibly choose dv and u in a way that we would be able to solve the equation. For example, for dv, it's preferred to pick dv in a way that v, the integral, would get us back the same value of v, like the exponential, okay? dv and v would give us the same value because the derivative and integral of ex always give us ex. So for u, it is equal to sin x, du equal to cosine x, dv equal ex, and v equal integral of ex dx, which is also ex. Now let I be the original integral within the question, and we will see why we need to differentiate this way. I is equal to integral of ex sin x dx. Again, u equal sin x, then du equal cosine x dx, dv equal ex dx, and v equal to ex. So I is equal to u v minus integral of v du, which is ex sin x minus integral of v times du, which is ex cosine x dx. Let's suppose that j is equal to integral ex cosine x dx. And we need to solve this one also. Let's work on j. So let's say that u is equal to cosine x, du equal to minus sin x, dv equal ex, hence v is also equal to integral ex dx, which is ex. So this solves into u times v, which is cosine x ex minus integral of v du, which is ex times minus sin x dx, correct? Now, minus can be removed to the outside, so you end up with ex cosine x plus integral of ex sine x dx. Now, notice something. What is that? This is the main question. This is I, correct? Hence, I is equal to j minus ex cosine x. Let's check it out. So again, I is equal to ex sin x minus integral of ex cosine x dx, which we named it j. And after solving j, also using the same pattern, but here u is equal to cosine x, du equal minus sine x, dv equal ex, and v equal ex. You end up with ex cosine x plus integral ex sine x dx, which is also I. You place this value of j back in the original equation, which is here. So you end up with I equal ex sin x minus j or minus ex cosine x plus this formula here, which is I. Now, this can be developed as I equal to ex sin x minus ex cosine x minus I. You can move I to the left, it becomes plus, so 2I is equal ex sin x minus ex cosine x. So 2I equal ex sin x minus times, like we factor it out as a common multiplier. 2I is equal to ex times sin x minus cosine x. Hence, I is equal to 1/2 ex sin x minus cosine x plus c. Since this integral happens to be a little bit complicated, I decided to solve it again in a more simplistic way, hopefully, to break it down to simpler parts. So, integral of ex sin x dx. To solve it, at first, we suppose that u is equal to sin x, du equal cosine x dx, dv is equal to ex dx, and v is equal to ex. So it is of the form integral u dv, okay, which is u is sin x here, and dv is equal to ex dx. It's equal to uv, or sin x ex, minus integral of v du, which is ex times cosine x dx. Now this part, we suppose that this is j. And the original integral, which is integral of ex sin x, is I. So what is j? Let us solve j apart. J is integral to of ex cosine x dx. Let's suppose that u is equal to cosine x, du equal minus sine x, dv is equal to ex, and v equal integral of ex, which is ex. So j is equal to uv, or cosine x ex, minus integral of v du, which is ex, times du is minus sine x dx. Now notice something. Minus can be removed because you can multiply it on the outside. You end up with cosine x ex plus integral of ex sin x dx. Now this quantity here is I. this is the original integral, correct? So you place j back into the original equation. Let's place j back. You have, and this is line 1 here. We place it back in 1. So I is equal to sin x ex minus j, correct? So sin x ex minus j, this is j, this quantity, minus cosine x ex minus I. Now I can be removed to the left, so you end up with 2i is equal to ex. We place it as a common multiplier times sin x minus cosine x. Hence, I is equal to 1/2 ex times sine x minus cosine x. And this is the final answer. Evaluate integral x ln x dx. So let's say u is equal to ln x, du equal 1 over x. dv is equal to x, then v is equal to integral of x, which is x squared over 2. dv is equal to x dx. Okay, so integral x ln x is equal to uv, which is x squared over 2 ln x, minus integral of v du, okay, which is x squared over 2, times du, which was 1 over x dx. So x squared over 2 ln x minus 1/2 x squared over x gives us x dx, which is x squared over 2. So x squared over 2 ln x minus x squared over 2, and you have 1/2 on the outside, so x squared over 4 plus c. Let's check it out. u equal ln x, du equal 1 over x dx, dv equal x dx, v equal x squared over 2. So integral x ln x dx is equal to x squared over 2 ln x minus 1/2 integral x dx equal x squared over 2 ln x minus x squared over 4 plus c. Integral of arctan x dx. Let's suppose u is equal to arctan x, du equal then to 1 over 1 plus x squared, part of the trig equations and functions, or trig formulas rather. dv equal dx, hence v is equal to x. Of course, du here is 1 over 1 plus x squared dx. So u is equal to arctan x, du equal 1 over 1 plus x squared, dv equal dx, v is equal to x. So the integral is equal to uv minus integral of v du, or x arctan x minus integral of v, which is x, times du, which is 1 over 1 plus x squared dx. If you notice, in the second integral, if we take, let's change its name here to omega. If we take omega as 1 plus x squared, so d omega becomes 2x dx. Hence, x dx is equal to d omega divided by 2. Let's replace them in the second integral. So it becomes x dx is equal to du over 2 divided by 1 plus x squared, which is omega, equal to 1/2 integral of d omega, not du, divided by omega, which is ln omega, 1/2 times ln omega, plus c. So omega is equal to 1 plus x squared, d omega equal to x dx. This becomes the second part, 1/2 ln 1 plus x squared, and then you plug it back into the original equation. We end up with the final answer, x arctan x minus 1/2 ln 1 plus x squared plus c. Integral of x squared ex dx. Okay, so u is equal to x squared, du equal to x dx, dv equal ex, and v is equal also ex. So this becomes x2 ex dx uv, or x squared ex, minus integral of v du, which is ex, times 2x, 2 you can take it to the outside, so ex times x dx. Now we need to solve it again, right? So for the second part, you need to again solve it. So let's say for the second integral, du equal x, du equal 1, dv equal ex, then v is equal to ex. So this second part becomes x2 ex minus 2 times, let's leave minus 2 on the outside, okay, uv, which is x ex, minus integral of v du, which is integral of ex dx, equal x2 ex minus 2x ex plus ex plus c. Here it might be clearer, so u equal x2 du equal 2x dx dv v. You end up with x squared ex minus 2 integral of x ex dx. Then we need to again solve it by parts. So you end up with, because this one is x ex dx, okay, so which is ex times x minus 1, or ex times x minus ex. So it is equal to x squared ex minus 2 ex times x plus 2 ex plus c. Integral from 0 to 1 of x ex dx. Straightforward. U equal x, du equal 1 times dx, dv equal ex, v equal ex. So it is uv, or x ex, minus integral of v du, which is ex dx, between 1 and 0, equal x ex minus ex, or ex multiplied by x minus 1 between 1 and 0. This gives us e times 1 minus 1 minus e0, which is 1, multiplied by 0 minus 1, which is minus 1, okay? So e times 1 minus 1, 0, and minus, I'm sorry, okay, it's a little bit ambiguous. So minus e0 multiplied by 0 minus 1, which is minus 1 times minus 1, or plus 1. So it is ex times x minus 1 between 1 and 0 equal plus 1. Integral x ln 2x dx. So u equal ln 2x. Du is equal to derivative of 2x divided by, so which is du over u. This is the derivative of ln u. Or supposedly that 2x is u, du is 2 over u, which is 2x. So this would be 1 over x. Now dv is equal to x, and v equal to x squared divided by 2. So this integral resolves into uv, or x squared over 2 ln 2x, minus integral of v du, which is x squared over 2 times 1 over x dx. 1 over 2, you can remove it to the outside, so we end up with x squared over 2 ln 2x minus 1 half integral of x dx. So x squared over 2 ln 2x minus 1 half x squared over 2, or minus 1/4 x squared plus c. Let's check it out. U equal ln 2x, du is equal to 1 over x dx, dv equal x dx, hence v equal x squared over 2. So it is equal to uv minus integral of v du. We solve it as we did moments ago. You end up with x squared over 2 ln 2x minus x squared over 4 plus c, which is correct. Tabular integration. Let's say you have an integral like the one here, and we don't want to repeat the integration by parts over and over when you have multiple layers that you need to go through. So this is how we solve it. You take x3, for example. Okay, so one part we need to differentiate over and over, and the other we need to integrate. So which one is the easiest to integrate? It is ex. Why? Because as long as you keep integrating it, it doesn't matter, it would keep giving you ex. For x3, it would resolve eventually into a finite value, a constant. So integral of x3 gives us 3x squared for the first time, then 6x, then finally 6. As for ex, you integrate first time, second time, third time. And here, okay, derivative of 6 gives us eventually 0 because it's a constant, and finally you have ex. And more than that, we need to alternate the sign, meaning that you multiply x3 times ex with a plus value, then second time minus value, then plus, then minus. Eventually we got to 0, so it no longer matters. So this resolves into the following value: x3 ex minus 3x squared ex plus 6x ex minus 6ex plus 0, doesn't matter, it becomes 0, plus c, which is the constant. Let's check it out if it's correct or not. So we differentiate x3, which becomes 3x squared, 6x, 6, then 0, and integrate ex. So ex is multiplying all of these values. You end up with ex times x3 minus 3x squared plus 6x minus 6 plus c, which is the same result that we've gotten. The only difference here is that he had taken ex as a common factor to all other components, plus the constant at the end. Integral between e and 1 of ln x dx. Now, as a short-handed way of solving this integral of ln x gives us always x ln x minus x. Now let's replace it with e and 1. So x ln x minus x between e and 1 gives us e ln e minus e minus 1 times ln 1, which is 0 minus 1, equal to ln e equal 1. So e minus e is 0, minus ln 1 is actually 0 also. You end up with minus 1 equal plus 1. This should be the final answer. And here's the solution. 1. Correct. If you recall, when we had an integral where we replaced an internal solution with j, okay, we called it j, and the outside integral was I, correct? And then we solved it for I. This is called a cyclic integral. And we have another example for that over here. So let's say u is equal to cosine x, du equal to minus sine x, dv equal ex, and v equal ex. So this solves into, at first, and let's call this integral as I. I is equal to uv, or ex cosine x, minus integral of v du, which is ex times minus sine x dx. Minus minus becomes plus, ex cosine x plus integral of ex sine x dx. And we will call this one j, and the one on the outside for which we need the solution as I. For the second time, for j, which is equal to integral ex sin x dx, u equal sin x, du equal cosine x, dv equal ex, and v equal ex. So this becomes ex sin x for j again, minus integral of v du, which is ex du, okay, times cosine x, correct, dx. Now this one is I, the original integral. So you move it to the left. Actually, we need to plug this quantity back over here, and we end up with, let me erase a little bit. So we need to plug this quantity back into its value here in j. So I is equal to ex cosine x plus this quantity, which is ex sine x, minus integral ex cosine x, which is I. So minus I, you move it back to the left, you end up with 2i. I is the one for which we need the solution, equal to ex times cosine x plus sine x. So I is equal to 1/2 ex multiplied by cosine x plus sine x. So by applying integration by parts twice, we got this solution. Integral of x for ex dx. Again, we go back to the tabular formula. So we need to differentiate x4 and integrate ex, then multiply them with an alternating sign. x4 becomes 4x3, then 12x squared, then 24x, then 24, then 0. ex is always ex, and we are integrating ex. Remember, first term is to be differentiated, second is to be integrated. ex, ex, ex. So we multiply with a plus sign, then with a minus sign, then with a plus sign, with a minus sign, with a plus sign. We end up with x4 ex minus 4x3 ex plus 12x squared ex minus 24x ex plus 24 ex plus a constant. And this is the final solution. Integral between 0 and pi of x sine x dx. U equal x, du equal dx, dv equal sine x, and v equal cosine x. Actually, minus cosine x. So this is equal to uv minus integral of v du. Okay, so x cosine x, actually minus cosine x, minus integral of v du, which is minus cosine x, times du is dx, between pi and 0. Here we can get rid of the minus sign because you have two minus on the inside and on the outside, so you multiply on the outside. Hence, minus x cosine x plus integral between 0 and pi cosine x dx equal to minus x cosine x. Integral of cosine gives us sine between pi and 0 equal minus pi. Cosine pi is minus 1, okay? Minus 1 plus sine pi 0 minus 0 and here 0. So it is equal to, okay, so the second part cancels out, equal to plus pi. And this is the final solution, pi. So integral x sine x dx is equal to minus x cosine x plus sine x between pi and 0. Integral x squared sine x dx. Okay, we can use the tabular method if you want. So we differentiate x squared and integrate sine x. This is to be integrated and here to be differentiated. Okay, so x squared becomes 2x, then 2, then 0. As for sine x, it alternates between cosine x, then minus sine x, then minus cosine x. That's enough. And here you multiply with alternating signs. So plus, then minus, then plus. Here no need to continue because you are multiplying by 0. You end up with x squared cosine x minus 2x minus sine x. It becomes plus 2 times minus cosine x plus c equal to x squared cosine x plus 2x sine x minus 2 cosine x plus a constant. And this is the final answer, minus x squared cosine x plus 2x sine x plus 2 cosine x plus c. Another note here is that the method that he had used was integrating by parts twice. But the tabular method is way much easier. That's why I resorted to it. I felt it was so much better. Definite exponential integral. Again, let's use the tabular method. So x squared, then 2x, then 2, then 0. Differentiating the first term. As for the second term, ex remains ex no matter how many times you integrate. Okay, so multiplying with a plus sign, then with a minus sign, then with a plus sign. We end up with x squared ex minus 2x ex plus 2ex between 1 and 0 equal, okay, so 1e minus 2e, e minus 2e plus 2e minus, we replace x by 0, so these first terms cancel out, and e0 is equal to 1 minus 2, okay? So minus 2e plus 2e is 0, which is equal to e minus 2. This is what is left. So it's equal to ex times x squared minus 2x plus 2 between 1 and 0 equal e minus 2. Integral of x arctan x dx. Now, we choose du is equal to arctan x, then du is equal to 1 over 1 plus x squared dx, dv is equal to x dx, hence v is equal to x squared over 2. So this is equal to uv minus integral of v du. uv is x squared over 2 arctan x minus v du, which is 1/2, you can remove it on the outside of the integral, x squared times 1 over 1 plus x squared dx. This one needs to be also resolved. This value can be broken down into 1 minus 1 over 1 plus x squared. So it would simplify the entire integral. Hence, it becomes the integral of 1 minus 1 over 1 plus x squared. Integral of 1 is x, and integral of 1 over 1 plus x squared is simply arctan. Hence, you end up with x squared plus 1 over 2 arctan x minus x over 2 plus c. Integral from 1 to 2, x ln x dx. u is equal to ln x, du equal 1 over x, dv equal to x, then v equal x squared over 2. So this becomes uv, or x squared over 2 times ln x minus integral of v du, which is x squared over 2 times du is 1 over x dx. All of that between 2 and 1, by the way. After that, we solve it between 2 and 1. So we replace x by 2. You end up with 2 to the power of 2 divided by 2, or 4 over 2, which is 2 ln 2 minus 4 over 4, or minus 1, minus, then you place 1 at the place of x. So ln 1, 0, minus 1 over 4. And the final answer is 2 ln 2 minus 3 over 4. Evaluate integral x squared ln x dx. Let's say u equal ln x, du equal 1 over x dx, dv equal x squared, v equal integral of x squared dx, which is x3 over 3. After that, we multiply uv, so this becomes uv minus integral v du, which is x3 over 3 ln x minus integral of x3 over 3 times du, which is 1 over x dx. x3 over 3 ln x minus 1/3 of integral x squared dx, which is x3 over 3. So this becomes x3 over 3 ln x minus x3 over 9 plus c. We end up with this final solution, x3 over 3 ln x minus x3 over 9 plus c. Module 7, Trigonometric Integrals. Starting with integral of sine to the power of 3x dx. Okay, so this one won't work by solving it in parts. Let's figure out how to solve it. First of all, this can be broken down into sin x multiplied by sin squared x. And here we need to refer back to the trig equations. These are the following. For cosine a plus b is equal to, and by the way, there's a rule of thumb. For cosine, it always multiplies with the same gender and it flips the sign. This is how I memorized them, okay, back in the days. So cosine a plus b is equal to cosine a, cosine b minus sine a, sine b. So it couples together and flips the habit or the sign, which is positive on the inside, it becomes negative on the outside. So for cosine a minus b, it is equal to, again, cosine a. cosine B plus, remember we flipped the sign, sine A sine B. As for the sign works oppositely, meaning that the sign on the sign, whether plus or minus for sinus, okay, for the sine is always preserved, and sine couples up with cosine and vice versa. In other words, sine A plus B becomes sine A cosine B plus cosine A sine B. So you have the same positive sign both on the inside of sine and to the right of the equation. As for sine A minus B becomes sine A cosine B minus cosine A sine B. For sine square x, this is actually sine A times sine B, where A is equal to B equal to x. So to get its value, we need to solve these two first equations by adding them up, but we need to also multiply by minus the first equation, lest we cancel out sine, correct? Because we need the sign here. So let's replace A and B by x at first. I'm gonna remove these two lines. First line is cosine A plus B, which is cosine x plus x or 2x equal cosine A cosine B, which is cosine square x, minus sine square x, which is sine x times sine x. As for the second equation, it is cosine A minus B, that would be cosine 0, which is 1, is equal to cosine square x plus sine square x, which we already know, by the way. Let's multiply by minus the first equation. So this becomes minus, this becomes plus, and we add 1 and 2 together. So you end up with, okay, cosine square x cancel out. So 2 sine square x is equal to 1 minus cosine 2x. Hence, sine square x is equal to 1 minus cosine 2x divided by 2. Then we need to multiply that with sine x. Okay, so you end up with sine x times 1 minus cosine 2x, and we will remove 1/2 to the outside. Okay, so now we end up also again with sine x multiplied by minus cosine 2x. So we also have to get rid of it for the second time. Or we use the following formula. So sin 3x is equal to sin x multiplied by sin square x, which is 1 minus cosine square x. So let's say u is equal to cosine x, du is equal to minus sine x dx, correct? Which means that, okay, integral of sine 3x dx becomes, okay, sine x is minus integral, so sine x dx is minus du, and here 1 minus cosine square x, which is 1 minus u squared. Hence, it becomes minus u minus u3 over 3 plus c, which is u3 over 3 minus u plus c. After that, we can reinstate the original value for u, which is cosine x. So you replace u by cosine x. We end up with minus cosine x plus cosine to the power of 3 of x divided by 3 plus c. Integral of cosine 5x dx. At first, cosine to the power of 5 can be broken down into cosine x times cosine 4x, which can also be written as cosine square x to the power of 2 equal to 1 minus sine square x square. Okay, let's suppose that u is equal to sine x, then du is equal to cosine x. Correct? So this becomes, if we convert it, okay, so du is equal to cosine x dx. Hence, this entire quantity over here becomes 1 minus, okay, remember u equals sine x, so 1 minus u square, all together square, times cosine x dx is du. Okay, so let's develop it. This is integral of 1 minus 2u square plus u 4 du equal to u plus, I'm sorry, let's fix that. So this is equal to u minus 2u to the power of 3 divided by 3 plus u5 over 5 plus c, with u equal to sine x. You simply replace it back. Again, cosine 5x can be rewritten as cosine x times cosine square x square, which is 1 minus sine square x square. U equals sine x, we suppose that. So du is equal to cosine x dx, which is this part here, multiplied by dx. Thus, integral of 1 minus u square square du. We develop it into integral of 1 minus 2y square plus u4 du, and we end up with u minus 2 u3 over 3 plus u5 over 5 plus c. Then you flip it back into sine x, which is the value of u. So sine x minus 2/3 sine 3 plus 1/5 sine 5 plus c. Integral of sin square x dx. Okay, so remember the trig equations. Cosine a plus b is equal to cosine a cosine b minus sine a sine b. Cosine a minus b equal to cosine a cosine b plus, as I mentioned before, you flip the sign, plus sine a sine b. Now here a equal b equal x, so let's develop that. It becomes cosine 2x is equal to cosine square x, because cosine x times cosine x, minus sine square x. Then cosine x minus x, which is cosine 0 or 1, is equal to cosine square x plus sine square x. We need to multiply the first equation by minus because we want to cancel out cosine, not the sine square x. Hence, sine square x or 2 sine square x, this is when you add the first and second equation. So 2 sine square x is equal to 1 minus cosine 2x. Hence, sine square x is equal to 1 minus cosine 2x divided by 2. And this is what is called the half angle identity. This is what people usually memorize without having to go through what I've gone through. I found my way a little bit better, okay? Even more memorable and more sophisticated. Therefore, so integral of sine square x dx can be replaced with 1/2 integral of 1 minus cosine 2x dx, which is x over 2 minus, okay, so integral of cosine 2x is simply 1 over 2 sine 2x. so sine x over 2, okay? And you have 1/2 from the outside, okay, multiplying x minus sine 2x over 2 plus c. As you multiply by 1/2, we end up with x over 2 minus sine 2x over 4 plus c. Another similar function, integral cosine squared x dx. So remember, cosine a plus b is equal to cosine a cosine b minus sine a sine b. Cosine a minus b is equal to cosine a cosine b plus sine a sine b. Always remember, with cosine, we flip the sign on the outside, and they go, the same genders go with each other. So cosine with cosine and sine with sine. Unlike sine a plus b, which goes, and sine a minus b. So which preserves the sign. So when it's positive on the inside, it is positive on the outside, plus sine goes with cosine. So sine is multiplied with cosine and vice versa. Here, a equal b equal x, so you have cosine 2x is equal to cosine squared x minus sine squared x. Cosine x minus x, which is cosine 0 or 1. Correct? So this is replaceable by 1. Equal cosine squared x plus sine squared x. We add these two equations together. What happens is these two cancel out. You end up with 2 cosine squared x is equal to 1 plus cosine 2x. Hence, cosine squared x is equal to 1 plus cosine 2x divided by 2. So you plug it back into the integral. Using this formula, let's integrate. Integral of cosine squared x dx is equal to 1/2, you can remove it to the outside, of integral of 1 plus cosine 2x, which is x, plus cosine, the integral is sine 2x, divided by 2. You multiply by 1/2, you end up with x over 2 plus sine 2x over 4 plus c, which is the final result. Integral of tan squared x dx. Now we need to use the formula tan squared x is equal to secant squared x minus 1, I think. Let's check it out. Yeah, tan squared x is equal to secant squared x minus 1. So you integrate secant squared x minus 1 dx. Now, integral of secant squared x is tan x, because the derivative of tan x gives us secant squared x. Hence, the final result is tan x minus x plus c. Integral of secant to the power of 3x dx. This we can break down into secant x multiplied by secant squared x. Okay, so if secant x is u, du equal secant x multiplied by tan x dx. As for dv equal secant squared x, so v equal integral of secant squared x dx, which is tan x. So let's apply this integral. Okay, uv secant x times tan x minus integral of v du, which is tan x, times secant x times tan x dx. So this becomes secant x tan x minus integral of tan squared x times secant x dx. As a side note, tan squared x, applying the Pythagorean rule, is equal to 1 minus secant squared x. So let's replace it. Hence, you get, okay, secant x, tan x minus integral of 1 minus secant square x multiplied by secant x dx. This finally resolves into I equal 1/2 secant x tan x plus 1/2 ln secant x plus tan x plus c. Integral of sine x cosine x dx. So sine x, let's say this is u, du is equal to cosine x dx. So straightforward, this part becomes du and sin x becomes u. Hence, it is integral of u du equal u squared over 2 plus c. Then we reinstate the original value of u, which is sine square x over 2 plus c. Let's check it out. Correct. Sine square x over 2 plus c. As simple as that. We simply performed a change of variable. So considering u equals sine x, du is equal to cosine x dx, which is this part of the integral. So this is du and this is u, straightforward. Integral sin 5x dx. This can be broken down into sin x multiplied by sin square x to the power of 2, which is 1 minus cosine square x to the power of 2. So it is sin x times 1 minus cosine square x square. All right, so if we consider u is equal to cosine square x, no, actually u is equal to, cosine x, rather. Du is equal to minus sine x dx, which is this part multiplied with dx. So sine x dx is equal to minus du. This becomes integral of sine x dx is minus du, so minus is left on the outside and we place du here, multiplied by 1 minus cosine square x. Cosine x is u. So 1 minus u square. Let's develop it. So it is minus integral of 1 minus 2u plus u, actually 1 minus 2u square plus u to the power of 4 du equal to, okay, let's multiply the minus right now. Integral of minus 1 plus 2u square minus u4 du equal u minus u plus 2u3 over 3 minus u5 divided by 5 plus c. Then you reinstate the original value of u, which is cosine x. So it is minus cosine x plus 2 cosine 3 x over 3 minus cosine 5 to the power of 5 of x over 5 plus c. Let's check it out. Okay, minus integral of 1 minus 2u squared plus u4 du, which is minus u plus 2u3 over 3 minus u5 over 5 plus c, and this is the final result. Correct. Evaluate integral of sine 3x cosine 2x dx. First of all, let's consider a equal 3x and b equal 2x to make it a little bit simpler, going back to the trig equations. As you remember, sine a plus b is equal to sine a cosine b plus cosine a sine b. Sine a minus b is equal to sine a cosine b minus cosine A sine B. If we add both equations together, these cancel out. You end up with 2 sine A cosine B is equal to sine A plus B plus sine A minus B. So sine A cosine B is equal to sine A plus B plus sine A minus B divided by 2. So the formula is sine 3x cosine 2x, basically, is equal to sine A plus B, which is sine 5x, plus sine A minus B, or sine x, divided by 2, and you place them back within the integral. This is the transformation. Hence, the integral is equal to, okay, 1/2 is placed on the outside of sine 5x plus sine x, all of that multiplied by the x, equal to 1/2 times 1/5 of minus cosine 5x minus cosine x, equal 1/10, actually minus 1/10 cosine 5x minus 1/2 cosine x plus c, which is the constant. Integral from 0 to pi sine square x dx. Okay, as a reminder, cosine A plus B is equal to cosine A cosine B minus sine A sine B. For cosine, we always pair the same gender together and we flip the sign from the outside. Cosine A minus B is equal to cosine A cosine B plus sine A sine B. A and B are equal to x in this case, but first we need to multiply by minus the first equation. So we end up with, okay, cosine A minus B, we are adding both equations, minus cosine A plus B, because this becomes minus, this minus, and this plus. So these two terms cancel out. Hence, cosine A minus B minus cosine A plus B is equal to 2 sine A sine B. Replacing A and B with x, so cosine 0, which is 1, minus cosine 2x is equal to 2 sine square x. Hence, sine square x is equal to 1/2 multiplied by 1 minus cosine 2x. So we place it back in the integral. This is 1/2 integral from 0 to pi, 1 minus cosine 2x dx, equal to 1/2 multiplied by x minus 1/2 sine 2x between pi and 0. We multiply the inside of the answer with 1/2, which was on the outside, and we evaluated between pi and 0. Now, sin 2 pi is equal to 0, and sin 0 equal to 0. So you end up with pi over 2. Exactly, it is pi over 2 minus sin 2 pi over 4 minus 0/2 minus sin 0/4. So all what is left is pi over 2. Same principle for cosine square x. Again, so as a reminder, you have cosine A plus B equal cosine A cosine B minus sine A sine B. Cosine A minus B is equal to cosine A cosine B plus sine A sine B. We add them together, you end up with 2 cosine square x in such case is equal to cosine 0, which is 1, plus cosine 2x. So cosine square x is rendered into 1 plus cosine 2x divided by 2. This becomes x over 2 plus integral of cosine 2x is sine 2x over 2. And you have also a multiplication of 1/2 between pi and 0, also equal to pi over 2. Mixed powers. Integral of sine square x cosine to the power of 3x dx. Now cosine 3x can be written as cosine x times cosine square x, or equal to cosine x times 1 minus sine square x. And don't forget about the sine square already multiplying cosine 3. Okay, so this is equal to, okay, the integral altogether becomes, on the inside, integral of sine square x times cosine x times 1 minus sine square x equal integral of cosine x times sine square x minus sine to the power of 4x dx. Let's say u is equal to sine x, then du is equal to cosine x dx. Thus, okay, cosine x dx becomes du, so you get integral of sine x is u, so it is integral of u squared minus u to the power of 4 times du equal to u3 over 3 minus u4, actually u4 becomes u5 over 5 plus c, and then you replace back u with sine x. So integral u squared minus u4 du equal u3 over 3 minus u5 over 5, which is sin 3x over 3 minus sin 5, or to the power of 5, divided by 5 plus c. Integral of secant x tan x dx. Now we know that derivative of secant x is equal to secant x times tan x. Correct? Hence, the integral for that, okay, derivative gives us secant x tan x dx. So the integral of that gives us back secant x. So the answer is secant of x plus c. Integral of cosecant x cotan x dx. Derivative of cosecant x is equal to minus cosecant x cotan x dx. Hence, integral of cosecant x cotan x dx gives us back minus cosecant x plus c. Tangent secant power integral. Okay, so here we notice that we have secant square x, which is, by the way, the derivative of tan x gives us back secant square x dx. So suppose that u equal tan x, du equal secant square x dx. We plug them back into this equation. So this is du, and here you have tan x to the power of 3, which is u to the power of 3. This becomes integral of u to the power of 3 du equal u4 over 4 plus c, with u being tan x. So the final answer is tan x to the power of 4 divided by 4 plus c. Again, u equal tan x, du equal secant square x dx. You plug them back into the equation. You end up with integral u3 du or u4 over 4 plus c, or tan x to the power of 4 divided by 4 plus c. Integral sin 4x dx. This is straightforward, okay? It's simply 1 over 4 times minus cosine 4x. But let us solve it classically, like using the entire methodology. Let's suppose u is equal to 4x. Then du becomes 4 dx. So dx is equal du divided by 4 as 4. Okay. Yeah, we have sin. Okay, so integral of sin u, which is 4x, times du, which is 4 dx. Okay, dx becomes du over 4. So 1 over 4 integral of sin u, which is minus cosine u, equal minus 1 over 4 cosine 4x plus c. u for x, du for dx. dx is equal to du over 4, and this is the final solution. Integral from 0 to pi over 2 sine 3x dx. First, we break it down into sine x multiplied by sine square x dx. Let's leave dx, which is on the inside of the integral. Sine square x is equal to 1 minus cosine square x. So sin x times 1 minus cosine square x dx. We suppose that u is equal to cosine x. So du is equal to minus sine x dx. So sine x dx is equal to minus du. Integral of minus du times 1 minus cosine square x becomes 1 minus u squared, because u is equal to cosine x. Now, as for the boundaries, remember, you have 0 and pi over 2 for x. So, since u is equal to cosine x, for x equals 0, the lower bound, u equal cosine 0, which is 1. X equal pi over 2, the upper bound, u is equal to cosine pi over 2, which is 0. So this becomes 1 to 0. We multiply by minus on the inside, integral from 1 to 0 of u squared minus 1 du equal u3 over 3 minus u between 0 and 1. This becomes minus, okay, 0 minus 1 plus 1/3 or 2 over 3. By the way, you can flip back u into its original value, which is cosine x, and then solve it for x. So we can keep the boundaries between 0 and pi over 2, whichever you like. So it's the same thing. We just need to pay attention not to mix them up together. Same thing for cosine to the power of 5x dx. So this can be written as cosine x multiplied by cosine square x squared, which is cosine x. And let's keep the dx also. So cosine x times 1 minus sine square x squared dx. So if u is equal to sine x, du is equal to cosine x dx. And this is cosine x dx. We replace them back, so cosine x dx becomes du multiplied by 1 minus sine x squared or u squared integral from, okay, we will keep the bound for now, okay, because we want to flip u back to its original value, which is sine x. So this becomes, let's develop on the inside, 1 minus 2u squared plus u to the power of 4 du equal to u minus 2u3 over 3 plus u5 over 5. We will reinstate the value of u, which is, okay, for an indefinite integral, you place plus c, but here we have boundaries, okay? Let's keep it for now. Equal sin x minus 2 sin x to the power of 3 divided by 3 plus sin x to the power of 5 divided by 5. Okay, sin x minus 2 third. Sin x to the power of 3 plus sin 5 x over 5 between pi over 2 and 0. For the lower bound, sin 0 is always 0, so we need to take care only with the upper bound. Sin x for x is equal to pi over 2 is simply 1. Hence, we end up with 1 minus 2 thirds plus 1 over 5 equal 8 over 15. Integral of sin 4x dx. Now, sin square x is equal to 1 minus cosine 2x divided by 2. We have sin 4x, so it is sin square x squared. We elevate the second part, squared, so you end up with 1 over 4 times 1 minus 2 cosine 2x plus cosine square 2x. Now, cosine square x is equal to 1 plus cosine 2x divided by 2. So cosine square 2x is equal to 1 plus cosine 4x over 2. Hence, we end up with 1 over 4 times 1 minus 2 cosine 2x plus 1 half plus cosine 4x over 2. You multiply 1/4, which is on the outside, with all the components. We end up with 3x over 8, after integrating, of course, minus sin 2x over 2, okay, which is the integral of cosine 2x, is sin 2x over 2. Integral of cosine 4x is equal to sin 4x divided by 4. 4 times 8, 32, plus c. Integral sin 3x times cosine 4x dx. Now sin 3x, sinus to the power of 3x can be rewritten as sin x times sin square x, which is also 1 minus cosine square x. Let's place it back within the integral. So integral of sin x times 1 minus cosine square x times cosine 4 to the power of 4x dx. We know that if u is equal to cosine x, du is equal to minus sine x dx. So sine x dx is equal to minus du. Let's replace them. So integral of, you can pull the minus to the outside, minus du times 1 minus cosine x is u. So cosine square x is u square times u to the power of 4 equal to integral of or minus integral of u4 minus u6 du, or plus integral of u6 minus u4 du, which is u7 over 7 plus u5 over 5. Let's check it out. So we end up with minus integral u4 times 1 minus u squared du, or minus integral u4 minus u6 du, or plus integral, as we said, u6 minus u4 du, equal to u7 over 7 minus u5 over 5 plus c. Then we need to reinstate the original value of u, which is cosine x. So it is u7 over 7 minus u5 over 5 plus c, or cosine 7x divided by 7 minus cosine 5x divided by 5. The order is irrelevant here. Okay, so, or we can say minus u5 over 5, which is minus cosine to the power of 5x divided by 5 plus cosine 7x divided by 7 plus c. 8 trigonometric substitutions. Exercise 1, integral involving square root of a square minus x square. Evaluate integral of square root of 4 minus x squared dx. First of all, let's suppose that x is equal to 2 cosine u. Okay, x equal to cosine u. Hence, dx becomes minus 2 sine u du. Let's plug them back into the integral. So you get integral of square root of 4 minus x squared is 4 cosine square u. That's why we chose it as 2 cosine u instead of cosine u. Multiplied by dx, which is minus 2 sine u du. Now, 4 can be removed to the outside. It becomes 2, multiplying the square root. So hence, integral of 2 square root of 1 minus cosine square u times minus 2 sine u du equal 2 times minus 2, this is minus 4, we remove it to the outside of the integral. Now, 1 minus cosine square u is simply equal to sine square u, correct? So this becomes square root of sine square u multiplied by sine u du. Square root of sine square u is sine u, so it is minus 4 integral of sine square u du, because sine u times square root of sine square u. Great, so once you get to this point, it should be straightforward. Sine square u is actually 1 minus cosine 2u divided by 2. And you replace it and you solve it in this way. So x is equal to sine theta, dx equal to cosine theta d theta. The same thing, actually you can solve it either ways. So square root of 4 minus x squared is equal to square root of 4 minus 4 sine square theta is equal to cosine theta. And we end up with 2 cosine theta to cosine theta. 4 square root of cosine square theta d theta, which is 1 plus cosine 2 theta over 2. So you end up with 4 over 2, which is 2 integral of 1 plus cosine 2 theta. So we can suppose that x is equal to 2 sine theta or 2 cosine theta. It works either ways. So the answer is 2 theta plus 2 over 2 sine 2 theta, which is 2 theta plus sine 2 theta plus c, okay? Since theta, now remember that x was equal to sine theta, correct? I forgot the proposition here, how he solved it actually. So yeah, theta was given as, or x rather, was given as 2 sine theta. Hence, theta is arc x over arc sin x over 2. So you place it back within the equation. Sin 2 theta is equal to sin theta cosine theta is equal to x square root of 4 minus x squared over 2. The answer is x over 2 square root of 4 minus x squared plus 2 arc sin x over 2 plus c. As a small clarification for sine 2 theta, which is in this equation. So x is equal to sine theta, correct? So sine 2 theta, which is equal to sine theta times cosine theta. Okay, now 2 sine theta is x. Cosine theta is actually, okay, given that cosine square theta plus sine square theta is equal to 1, correct? So cosine theta is equal to square root of 1 minus sine square theta. This is where we got it from. Hence, cosine theta is square root of 1 minus sine square theta. What is sine square theta? X over 2, okay? X squared over 4, actually, because x equal 2 sine theta. Hence, sine square theta is x squared over 4. So you multiply 4 here, you end up with 4 minus x squared over 4, and 1 over 4 is removed to the outside of the square root. So you end up with 1/2 x square root of 4 minus x squared. And this is the solution here for sine 2 theta. You add them together. You add 2 theta plus 2 plus sine 2 theta plus c. That's why. Thank you for watching, and I hope that you enjoyed this session, and see you next time.